Welcome to AI Engineering, Building Applications with Foundation Models. Chapter 1, Introduction to Building AI Applications with Foundation Models. If I had to use just one word to describe the world of AI after 2020, that word would be scale. The AI models that power applications like ChatGPT, Google's Gemini, and Midjourney are now so large that they consume a significant portion of the world's electricity. We're even at risk of running out of publicly available data on the internet to train them. This incredible scaling of AI models has led to two major consequences. First, these models are becoming more powerful and capable of handling a wider range of tasks, which in turn enables more applications. This means more people and teams are using AI to boost productivity, create economic value, and improve our quality of life. Second, training these massive models requires vast amounts of data, computing power, and specialized talent that only a handful of organizations can afford. This has led to the rise of what we call model as a service. Models developed by these few organizations are now available for others to use as a service. So, if you want to build an AI application, you can now use these powerful models without having to invest in building one from scratch. In short, the demand for AI applications has skyrocketed, while the barrier to entry for building them has dropped. This has turned AI engineering, the process of building applications on top of these readily available models, into one of the fastest growing fields in engineering. Of course, building applications with machine learning, or ML, models isn't new. Long before large language models became mainstream, AI was already powering many applications you might be familiar with, like product recommendations, fraud detection, and churn prediction. While many of the core principles for putting AI into production remain the same, this new generation of large-scale, accessible models brings new possibilities and new challenges. And that's what this audiobook is all about. This first chapter will start with an overview of foundation models, which are the key drivers behind the explosion of AI engineering. Then I'll walk you through a range of successful AI use cases to give you a feel for what AI is good at and where it still has room to grow. As AI's capabilities expand daily, predicting its future is becoming tougher, but looking at existing application patterns can help us uncover opportunities today and give us clues about where AI is headed. To wrap up this chapter, I'll give you an overview of the new AI stack, highlighting what has changed with foundation models, what has stayed the same, and how the role of an AI engineer today is different from that of a traditional ML engineer. Let's begin with the rise of AI engineering. Foundation models didn't appear out of nowhere. They grew out of large language models, which themselves originated from simpler language models. While applications like ChatGPT and GitHub's Copilot might seem like they burst onto the scene overnight, they are actually the result of decades of technological advancements, with the first language models emerging way back in the 1950s. Let's trace the key breakthroughs that took us from those early language models to the discipline of AI engineering today. First, let's talk about the journey from language models to large language models. Although language models have been around for a while, they've only recently grown to their current massive scale, thanks to a technique called self-supervision. This section will give you a quick overview of what a language model is and what self-supervision means. If you're already familiar with these concepts, feel free to skip ahead. So what is a language model? At its core, a language model encodes statistical information about one or more languages. This information essentially tells us how likely a word is to appear in a given context. For example, if you have the sentence, "My favorite color is," a language model that understands English should predict the word blue much more often than the word car. The statistical nature of languages was discovered centuries ago. In the 1905 story, The Adventure of the Dancing Men, Sherlock Holmes used simple statistical information about English to decode a sequence of mysterious stick figures. He knew that the most common letter in English is E, so he deduced that the most common stick figure must represent E. Later, Claude Shannon used more sophisticated statistics to decipher enemy messages during World War II. His work on modeling the English language was published in his famous 1951 paper, Prediction and Entropy of Printed English. Many concepts from that paper, like entropy, are still used in language modeling today. In the early days, a language model dealt with just one language. Today, however, a language model can handle multiple languages. The basic unit of a language model is a token. A token can be a character, a word, or even part of a word, like Huyen, depending on the model. For instance, GPT-4, one of the models behind ChatGPT, breaks the phrase "I can't wait to build AI applications" into 9 tokens. In this example, the word can't is split into 2 tokens, can and t. The process of breaking text into tokens is called tokenization. For GPT-4, an average token is about 3/4 the length of a word. So 100 tokens would be roughly 75 words. The complete set of all tokens that a model can work with is called its vocabulary. You can use a small number of tokens to create a vast number of different words, much like how you use the letters of the alphabet to form many words. For example, the Mixtral 8x7b model has a vocabulary of 32,000 tokens, while GPT-4's vocabulary is over 100,000. The tokenization method and vocabulary size are decided by the model's developers. You might be wondering why language models use tokens instead of words or characters. There are 3 main reasons. First, compared to characters, tokens allow the model to break words into meaningful parts. For instance, cooking can be split into cook and in, with both parts carrying some meaning of the original word. Second, since there are fewer unique tokens than unique words, this reduces the model's vocabulary size, making it more efficient. Finally, tokens help the model process words it has never seen before. A made-up word like chat-GPT could be split into chat-GPT and ing, helping the model understand its structure. Tokens strike a balance, retaining more meaning than individual characters while being more efficient than whole words. There are 2 main types of language models: masked language models and autoregressive language models. The key difference is the information they use to predict a token. A masked language model is trained to predict missing tokens anywhere in a sequence, using the context from both before and after the missing token. Essentially, it's trained to fill in the blanks. For example, given the sentence, "My favorite color is blue," a masked language model should predict that the blank is likely color. A well-known example of this type is BERT. Today, masked language models are commonly used for tasks like sentiment analysis and text classification, or for tasks that require understanding the full context, like code debugging. An autoregressive language model, on the other hand, is trained to predict the next token in a sequence, using only the tokens that come before it. It tries to predict what comes next in a sentence, like, "My favorite color is..." An autoregressive model can continuously generate one token after another. Today, these are the models of choice for text generation, which is why they are much more popular. In this audiobook, unless I say otherwise, when I mention language model, I'll be referring to an autoregressive model. The outputs of language models are open-ended. A model can use its fixed, finite vocabulary to construct an infinite number of possible outputs. A model that can generate open-ended outputs is called generative, which is where the term generative AI comes from. You can think of a language model as a completion machine. You give it some text or a prompt, and it tries to complete that text. For example, if your prompt is "to be or not to be," the model might complete it with "that is the question." It's important to remember that these completions are predictions based on probabilities, and they're not always guaranteed to be correct. This probabilistic nature is what makes language models both so exciting and frustrating to use, something we'll explore more in Chapter 2. As simple as it sounds, this completion ability is incredibly powerful. Many tasks, including translation, summarization, coding, and even solving math problems, can be framed as completion tasks. For example, if you give a model the prompt, "How are you in French is," it might complete it with "Comment ça va," effectively translating from one language to another. Similarly, if you prompt it with a question like, "Is this email likely spam? Here's the email content, answer," it might complete it with "likely spam," turning the language model into a spam classifier. While completion is powerful, it's not the same as having a conversation. For example, if you ask a completion machine a question, it might just complete what you said by adding another question instead of answering yours. We'll discuss how to make a model respond appropriately to a user's request later in the audiobook. Now let's talk about self-supervision. Language modeling is just one of many machine learning algorithms. There are models for all sorts of things, like object detection, recommender systems, and weather forecasting. So what's so special about language models that made them the center of the scaling approach that led to the ChatGPT moment? The answer is that language models can be trained using self-supervision, while many other models require supervision. Supervision is the process of training ML algorithms using labeled data, which can be expensive and slow to get. Self-supervision helps overcome this data labeling bottleneck, allowing us to create much larger data sets for models to learn from, which in turn allows the models to scale up. Here's how it works. With supervision, you provide labeled examples to show the model the behavior you want it to learn. Once trained, the model can be applied to new data. For example, to train a fraud detection model, you'd use examples of transactions, each labeled as either fraud or not fraud. The model learns from these examples and can then predict whether a new transaction is fraudulent. The success of AI models in the 2010s was largely due to supervision. The model that kickstarted the deep learning revolution, AlexNet, was supervised. It was trained to classify over 1 million images from the ImageNet dataset into one of 1,000 categories, like car, balloon, or monkey. The downside of supervision is that data labeling is expensive and time-consuming. If it costs 5 cents to have one person label one image, it would cost $50,000 to label 1 million images for ImageNet. If you want 2 people to label each image to cross-check for quality, the cost doubles. To expand the model's capabilities to more objects, you'd need to add more categories. Scaling up to 1 million categories could cost $50 million in labeling alone. Labeling everyday objects is something most people can do without much training, so it's relatively cheap. But not all labeling tasks are that simple. Generating Latin translations for an English to Latin model is more expensive. Labeling whether a CT scan shows signs of cancer would be astronomically costly. Self-supervision helps overcome this data labeling bottleneck. In self-supervision, the model can infer labels from the input data itself instead of requiring explicit labels. Language modeling is self-supervised because each input sequence provides both the labels, the tokens to be predicted, and the context the model can use to predict them. For example, the sentence, "I love street food," can provide 6 training samples. The first input would be a beginning of sequence marker, and the output would be I. The next input would be the beginning marker and I, and the output would be love. This continues until the end of the sentence, marked by an end-of-sequence token. These markers are essential for a language model to work with multiple sequences and are typically treated as special tokens by the model. The end-of-sequence marker is particularly important because it helps the model know when to stop its response. It's important to note that self-supervision is different from unsupervision. In self-supervised learning, labels are inferred from the data. In unsupervised learning, you don't need labels at all. Because of self-supervised learning, language models can learn from text sequences without any manual labeling. Since text is everywhere, in books, blog posts, articles, and Reddit comments, it's possible to create a massive amount of training data. This has allowed language models to scale up and become what we now call large language models, or LLMs. LLM, however, is not a very scientific term. How large does a language model have to be considered large? What's considered large today might be tiny tomorrow. A model's size is typically measured by its number of parameters. A parameter is a variable within a model that gets updated during training. Generally, though not always, the more parameters a model has, the greater its capacity to learn. When OpenAI's first GPT model came out in June 2018, it had 117 million parameters, which was considered large at the time. Then, in February 2019, OpenAI introduced GPT-2 with 1.5 billion parameters, and suddenly 117 million was considered small. As of this writing, a model with 100 billion parameters is considered large. Perhaps one day even that will seem small. Before we move on, I want to touch on a question that's often taken for granted. Why do larger models need more data? It might seem counterintuitive. If a model is more powerful, shouldn't it need fewer examples to learn? The reason is that larger models have a greater capacity to learn, so they need more training data to maximize their performance. You could train a large model on a small dataset, but it would be a waste of computing power. You could likely achieve similar or better results on that dataset with a smaller model. Now let's talk about the transition from large language models to foundation models. While language models are incredibly capable, they are limited to text. As humans, we experience the world through more than just language. We use vision, hearing, touch, and more. For AI to operate effectively in the real world, it needs to be able to process data beyond text. For this reason, language models are being extended to handle more data modalities. Models like GPT-4v and Claude 3 can understand both images and text. Some models can even process videos, 3D assets, protein structures, and more. Adding these extra modalities makes them even more powerful. In fact, OpenAI noted in 2023 that incorporating additional modalities, like image inputs, is a key frontier in AI research. While many people still call models like Gemini and GPT-4v LLMs, a better term for them is foundation models. The word foundation signifies both their importance in AI applications and the fact that they can be built upon for various needs. Foundation models represent a major shift from the traditional structure of AI research. For a long time, AI research was divided by data types. Natural language processing, or NLP, dealt only with text. Computer vision dealt only with images. Text-only models were used for tasks like translation and spam detection, while image-only models handled object detection and image classification. Audio-only models managed speech-to-text and text-to-speech. A model that can work with more than one data modality is called a multimodal model. A generative multimodal model is also called a large multimodal model, or LMM. While a language model generates the next token based only on previous text tokens, a multimodal model can generate the next token using information from both text and image tokens, or whatever other modalities it supports. Just like language models, multimodal models need a lot of data to scale up, and self-supervision works for them too. For example, OpenAI used a technique called natural language supervision to train their language image model, CLIP. Instead of manually labeling each image, they collected pairs of images and text that appeared together on the internet. They were able to create a dataset of 400 million image-text pairs, which was 400 times larger than ImageNet, without any manual labeling costs. This dataset allowed CLIP to become the first model that could generalize to multiple image classification tasks without needing additional training. This audiobook will use the term foundation models to refer to both large language models and large multimodal models. It's important to note that CLIP isn't a generative model. It wasn't trained to produce open-ended outputs. CLIP is an embedding model trained to create joint embeddings of both text and images. We'll discuss embeddings in more detail later, but for now, you can think of them as numerical vectors that capture the meaning of the original data. Multimodal embedding models like CLIP are the backbone of generative multimodal models, such as Flamingo, Lava, and Gemini. Foundation models also mark a shift from task-specific models to general-purpose models. Previously, models were often developed for specific tasks like sentiment analysis or translation. A model trained for sentiment analysis couldn't do translation, and vice versa. Foundation models, thanks to their scale and training methods, are capable of a wide range of tasks right out of the box. A single LLM can perform both sentiment analysis and translation. However, you can often tweak a general-purpose model to maximize its performance on a specific task. For example, imagine you're working with a retailer to build an application that generates product descriptions for their website. An out-of-the-box model might be able to generate accurate descriptions, but it might not capture the brand's voice or highlight its key messages. The descriptions might even be full of cliches and marketing jargon. There are several techniques you can use to get the model to generate what you want. For example, you can craft detailed instructions with examples of desirable product descriptions. This approach is called prompt engineering. You could also connect the model to a database of customer reviews that it can use to generate better descriptions. Using a database to supplement the instructions is called Retrieval Augmented Generation, or RAG. Another option is to fine-tune, or further train, the model on a dataset of high-quality product descriptions. Prompt engineering, RAG, and fine-tuning are three very common AI engineering techniques for adapting a model to your needs. We'll discuss all of them in detail throughout this audiobook. Adapting an existing powerful model for your task is generally much easier than building one from scratch. For example, it might take just 10 examples in a weekend compared to 1,000,000 examples in 6 months. Foundation models make it cheaper and faster to develop AI applications. Exactly how much data you need to adapt a model depends on the technique you use, and we'll touch on that as we discuss each one. However, there are still many benefits to task-specific models. For example, they might be much smaller, making them faster and cheaper to use. Whether to build your own model or use an existing one is a classic buy or build question that teams have to answer for themselves. The discussions throughout this audiobook will help you make that decision. This brings us to the shift from foundation models to AI engineering. AI engineering is the process of building applications on top of foundation models. People have been building AI applications for over a decade, a process often known as ML engineering or ML ops. So why are we talking about AI engineering now? The key difference is that traditional ML engineering often involves developing ML models from scratch, while AI engineering leverages existing ones. The availability of powerful foundation models has created the perfect conditions for the rapid growth of AI engineering as a discipline due to three main factors. First, we have general-purpose AI capabilities. Foundation models are powerful not just because they can do existing tasks better, but also because they can do more tasks. Applications that were once thought impossible are now possible, and new applications are emerging all the time. This makes AI more useful in more aspects of life, vastly increasing both the user base and the demand for AI applications. For example, since AI can now write as well as humans, and sometimes even better, it can automate or partially automate almost every task that requires communication. AI is being used to write emails, respond to customer requests, and explain complex contracts. Anyone with a computer can now access tools to instantly generate customized, high-quality images and videos for marketing materials, professional headshots, art concepts, book illustrations, and more. AI can even be used to synthesize training data, develop algorithms, and write code, which will help train even more powerful models in the future. The second factor is increased AI investments. The success of ChatGPT led to a sharp increase in investments in AI from both venture capitalists and large companies. As AI applications become cheaper and faster to bring to market, the return on investment becomes more attractive. Companies are rushing to incorporate AI into their products and processes. Goldman Sachs research estimated that AI investment could approach $100 billion in the US and $200 billion globally by 2025. AI is now frequently mentioned as a competitive advantage. In fact, FactSet found that 1 in 3 S&P 500 companies mentioned AI in their earnings calls in the second quarter of 2023, 3 times more than the year before. The third factor is the low barrier to entry for building AI applications. The model-as-a-service approach, popularized by OpenAI and other model providers, makes it incredibly easy to leverage AI. In this approach, models are accessed through APIs that receive user queries and return model outputs. This means you can access powerful models with just a single API call without needing the infrastructure to host and serve them yourself. Not only that, AI also makes it possible to build applications with minimal coding. First, AI can write code for you, allowing people without a software engineering background to quickly turn their ideas into reality. Second, you can interact with these models using plain English instead of a programming language. This means anyone, and I mean anyone, can now develop AI applications. Because of the massive resources required to develop foundation models, this process is only possible for big corporations like Google and Meta, governments, and well-funded startups like OpenAI. In a 2022 interview, Sam Altman, the CEO of OpenAI, said that the biggest opportunity for most people will be to adapt these models for specific applications. The world has quickly embraced this opportunity. AI engineering has rapidly become one of the fastest-growing engineering disciplines. Tools for AI engineering are gaining traction faster than any previous software engineering tools. Within just 2 years, 4 open-source AI engineering tools, AutoGPT, Stable Diffusion Web UI, LangChain, and Allama, have already garnered more stars on GitHub than Bitcoin. They are on track to surpass even the most popular web development frameworks, like React and Vue. A LinkedIn survey from August 2023 showed that the number of professionals adding terms like generative AI, ChatGPT, and prompt engineering to their profiles increased by an average of 75% each month. Computer World even declared that teaching AI to behave is the fastest-growing career skill. You might be wondering why I'm using the term AI engineering. Many terms are being used to describe this process, like ML engineering, ML ops, AI ops, and LM ops. I chose AI engineering for a few reasons. I didn't go with ML engineering because, as we'll discuss later, working with foundation models is different from working with traditional ML models in several important ways. I didn't go with terms ending in ops because while there are operational components, the focus is more on engineering or tweaking foundation models to do what you want. Finally, I surveyed 20 people who were developing applications with foundation models, and most of them preferred the term AI engineering, so I decided to go with the people. The rapidly expanding community of AI engineers has shown remarkable creativity with an incredible range of exciting applications. In the next section, we'll explore some of the most common application patterns. Now, let's look at some common use cases for foundation models. If you're not already building AI applications, I hope the previous section has convinced you that now is a great time to start. If you already have an application in mind, you might want to jump ahead to the section on planning AI applications. But if you're looking for inspiration, this section covers a wide range of industry-proven and promising use cases. The number of potential applications you could build with foundation models seems endless. Whatever you can think of, there's probably an AI for that. It's impossible to list all the potential use cases, and even categorizing them is a challenge. Different surveys use different categories. For example, Amazon Web Services categorizes enterprise use cases into 3 buckets: customer experience, employee productivity, and process optimization. A 2024 O'Reilly survey listed 8 categories, including programming, data analysis, and customer support. Some organizations like Deloitte categorize use cases by the value they create, such as cost reduction or accelerating innovation. Gartner even has a category for business continuity, meaning a company might go out of business if it doesn't adopt generative AI. In a 2023 survey of 2,500 executives, 7% cited business continuity as their motivation for embracing it. A study by Alaundu and others in 2023 provides excellent research on how exposed different occupations are to AI. They defined a task as exposed if AI can reduce the time needed to complete it by at least 50%. According to the study, occupations with nearly 100% exposure include interpreters, translators, tax preparers, web designers, and writers. On the other hand, occupations with no exposure to AI include cooks, stonemasons, and athletes. This gives a good idea of what AI is good for. When analyzing use cases, I looked at both enterprise and consumer applications. To understand enterprise use cases, I interviewed 50 companies and read over 100 case studies. For consumer applications, I examined over 200 open-source AI applications on GitHub. I've categorized them into 8 groups, which should serve as a helpful reference. The categories are coding, image and video production, writing, education, conversational bots, information aggregation, data organization, and workflow automation. An application can belong to more than one category. For example, a bot can provide companionship and also aggregate information. Among open-source applications, the most popular use cases are coding, image and video production, and conversational bots. The enterprise world generally prefers applications with lower risks. For example, a 2024 report showed that companies are quicker to deploy internal-facing applications, like knowledge management, than external-facing ones, like customer support chatbots. This allows them to develop their AI expertise while minimizing risks related to data privacy and compliance. Even after seeing hundreds of AI applications, I'm still surprised by new ones every week. In the early days of the internet, few could have predicted that social media would become its dominant use case. As we learn to make the most of AI, the use case that will eventually dominate might surprise us all. Hopefully, it will be a good surprise. Now, let's explore these categories in more detail, starting with coding. In multiple generative AI surveys, coding is by far the most popular use case. This is both because AI is good at coding and because early AI engineers are coders themselves. One of the earliest successes of foundation models in production is GitHub Copilot, a code completion tool whose annual recurring revenue crossed $100 million just 2 years after its launch. AI-powered coding startups have raised hundreds of millions of dollars, and open-source tools like GPT Engineer and Screenshot to Code gained tens of thousands of stars on GitHub within a year. Besides general coding tools, many specialize in certain tasks. For example, there are tools for extracting structured data from web pages, converting English to code, generating website code from a design or screenshot, translating between programming languages, writing documentation, creating tests, and even generating commit messages. It's clear that AI can do many software engineering tasks. The question is whether AI can automate software engineering altogether. On one end of the spectrum, NVIDIA's CEO, Jensen Huang, predicts that AI will replace human software engineers and that we should stop telling kids to learn to code. On the other end, many software engineers are convinced they will never be replaced by AI for both technical and emotional reasons. Software engineering consists of many tasks, and AI is better at some than others. McKinsey researchers found that AI can help developers be twice as productive for documentation and 25 to 50% more productive for code generation and refactoring. However, they observed minimal productivity improvement for highly complex tasks. Many developers of AI coding tools have also told me that AI is much better at front-end development than back-end development. Regardless of whether AI will replace software engineers, it can certainly make them more productive. This means companies can now accomplish more with fewer engineers. AI could also disrupt the outsourcing industry, as outsourced tasks tend to be simpler ones outside a company's core business. Next, let's talk about image and video production. Thanks to its probabilistic nature, AI is great for creative tasks. Some of the most successful AI startups are creative applications, such as Midjourney for image generation, Adobe Firefly for photo editing, and Runway and Sora for video generation. In late 2023, just a year and a half after its launch, Midjourney had already generated $200 million in annual recurring revenue. As of December 2023, half of the top 10 free graphics and design apps on the Apple App Store had AI in their names. I suspect that soon, all graphics and design apps will incorporate AI by default, and they won't even need to mention it. It's now common to use AI to generate profile pictures for social media, from LinkedIn to TikTok. Many candidates believe that AI-generated headshots can help them put their best foot forward and increase their chances of landing a job. The perception of AI-generated profile pictures has changed significantly. In 2019, Facebook banned accounts using them for safety reasons. By 2023, many social media apps were providing tools for users to create them. For businesses, ads and marketing have been quick to incorporate AI. It can be used to generate promotional images and videos directly, brainstorm ideas, or create first drafts for human experts to refine. You can use AI to generate multiple ad variations and test which ones work best for your audience. AI can even generate variations of your ads based on seasons and locations, like changing leaf colors in the fall or adding snow in the winter. Now let's move on to writing. AI has long been used to help with writing, If you use a smartphone, you're probably familiar with autocorrect and autocompletion, both powered by AI. Writing is an ideal application for AI because we do it a lot. It can be tedious, and we have a high tolerance for mistakes. If a model suggests something you don't like, you can just ignore it. It's no surprise that LLMs are good at writing, given that they are trained for text completion. An MIT study found that professionals who used ChatGPT for writing tasks completed them 40% faster and produced output that was 18% higher in quality. The study also noted that ChatGPT helps close the quality gap between workers, meaning it's most helpful for those who are less inclined to writing. For consumers, the use cases are obvious. Many use AI to help them communicate better. You can write an angry email and ask AI to make it sound pleasant. You can give it bullet points and get back complete paragraphs. Students are using AI to write essays, and writers are using it to write books. Many startups are already using AI to generate children's books, fan fiction, and romance novels. Unlike traditional books, AI-generated books can be interactive, with the plot changing based on a reader's preference. However, AI's ability to write can also be abused. In 2023, the New York Times reported that Amazon was flooded with shoddy AI-generated travel guidebooks, complete with fake author bios, websites, and rave reviews, all generated by AI. For businesses, AI writing is common in sales, marketing, and team communication. Many managers have told me they use AI to help write performance reports. AI can craft effective cold outreach emails, ad copy, and product descriptions. CRM apps like HubSpot and Salesforce also have tools for generating web content and outreach emails. AI seems particularly good at search engine optimization, or SEO, perhaps because many AI models are trained on internet data, which is full of SEO-optimized text. AI is so good at it that it has enabled a new generation of content farms. These farms set up junk websites, fill them with AI-generated content to rank high on Google, and then sell advertising spots. Unless something is done to curb this, the future of internet content could be bleak and AI-generated. Let's discuss education next. Whenever ChatGPT is down, OpenAI's Discord server is flooded with students complaining about being unable to complete their homework. Several school districts, including New York City and Los Angeles, initially banned ChatGPT over fears of cheating, but reversed their decisions just a few months later. Instead of banning AI, schools could incorporate it to help students learn faster. AI can summarize textbooks and generate personalized lecture plans for each student. I find it strange that ads are personalized because we know everyone is different, but education often isn't. AI can adapt materials to the format best suited for each student. Auditory learners can ask AI to read materials out loud. Students who love animals can have visualizations adapted to feature more animals. Those who find it easier to read code than math equations can ask AI to translate equations into code. AI is especially helpful for language learning, as you can ask it to role-play different practice scenarios. Duolingo found that out of the 4 stages of course creation, lesson personalization is the stage that can benefit the most from AI. AI can generate quizzes, both multiple choice and open-ended, and evaluate the answers. It can become a debate partner, as it's much better at presenting different views on the same topic than the average human. Khan Academy, for example, offers AI-powered teaching assistants to students and course assistants to teachers. An innovative teaching method I've seen is where teachers assign AI-generated essays for students to find and correct mistakes. While many education companies are embracing AI to build better products, others are finding their business models disrupted. Chegg, a company that helps students with their homework, saw its share price plummet after ChatGPT launched, as students turned to AI for help instead. If the risk is that AI could replace many skills, the opportunity is that AI can be used as a tutor to learn any skill. For many skills, AI can help someone get up to speed quickly, allowing them to continue learning on their own to become even better than the AI. Now let's talk about conversational bots. Conversational bots are incredibly versatile. They can help us find information, explain concepts, and brainstorm ideas. AI can be your companion and even your therapist. It can emulate personalities, letting you talk to a digital copy of anyone you like. Digital girlfriends and boyfriends have become surprisingly popular in a short amount of time, with many people already spending more time talking to bots than to humans. For businesses, the most popular bots are customer support bots. They can help companies save costs while improving customer experience by responding to users faster than human agents. AI can also act as product co-pilots, guiding customers through confusing tasks like filing insurance claims or doing taxes. The success of ChatGPT prompted a wave of text-based conversational bots. However, text isn't the only interface. Voice assistants like Google Assistant, Siri, and Alexa have been around for years. 3D conversational bots are already common in games and are gaining traction in retail and marketing. One exciting use case is smart NPCs, or non-player characters, in video games. AI can make these NPCs much smarter, changing the dynamics of existing games like The Sims and Skyrim and enabling entirely new games. Next up is information aggregation. Many people believe that success depends on our ability to filter and digest useful information. However, keeping up with emails, Slack messages, and news can be overwhelming. Luckily, AI has proven to be excellent at aggregating and summarizing information. According to Salesforce's 2023 research, 74% of generative AI users use it to distill complex ideas and summarize information. For consumers, many applications can process your documents, like contracts and papers, and let you retrieve information in a conversational way. This use case is often called "talk to your docs." AI can help you summarize websites, conduct research, and create reports on topics of your choice. During the process of writing this audiobook, I found AI very helpful for summarizing and comparing papers. For businesses, information aggregation is essential for operations. More efficient information flow can help an organization become leaner by reducing the burden on middle management. When Instacart launched an internal prompt marketplace, they discovered that one of the most popular templates was Fast Breakdown, which asks AI to summarize meeting notes, emails, and Slack conversations into facts, open questions, and action items. These action items can then be automatically inserted into a project tracking tool and assigned to the right people. AI can also help you surface critical information about potential customers and analyze your competitors. Now let's discuss data organization. One thing is certain about the future. We'll continue to produce more and more data. Smartphone users will keep taking photos and videos, and companies will continue to log everything about their products, employees, and customers. It's essential to organize all this unstructured data so it can be searched later. AI can help with exactly that. It can automatically generate text descriptions for images and videos, or help match text queries with visuals. Services like Google Photos are already using AI to surface images that match search queries. Google Image Search even takes it a step further. If there's no existing image that matches a user's need, it can generate one. AI is also very good at data analysis. It can write programs to generate data visualizations, identify outliers, and make predictions like revenue forecasts. Businesses can use AI to extract structured information from unstructured data, which can then be used to organize and search that data. Simple use cases include automatically extracting information from credit cards, driver's licenses, and receipts. More complex use cases include extracting data from contracts, reports, and charts. It's estimated that the intelligent data processing industry will reach nearly $13 billion by 2030, growing over 30% each year. Finally, let's cover workflow automation. Ultimately, AI should automate as much as possible. For end users, automation can help with boring daily tasks like booking restaurants, requesting refunds, planning trips, and filling out forms. For businesses, AI can automate repetitive tasks such as lead management, invoicing, reimbursements, and data entry. One especially exciting use case is using AI models to synthesize data, which can then be used to improve the models themselves. You can use AI to create labels for your data, with humans in the loop to improve the labels. We'll discuss data synthesis in Chapter 8. To accomplish many of these tasks, AI needs access to external tools. To book a restaurant, an application might need permission to open a search engine, use your phone to make calls, and add appointments to your calendar. AIs that can plan and use tools are called agents. The level of interest around agents borders on obsession, but it's not entirely unwarranted. AI agents have the potential to make every person vastly more productive and generate enormous economic value. Agents will be a central topic in Chapter 6. It's been a lot of fun looking into different AI applications. However, not all applications should be built. The next section will discuss what we should consider before building one. Now we move on to planning AI applications. Given the seemingly limitless potential of AI, it's tempting to jump right into building applications. If you just want to learn and have fun, then by all means jump right in. Building is one of the best ways to learn. In the early days of foundation models, several heads of AI told me they encouraged their teams to experiment with AI applications just to upskill themselves. However, if you're building for a living, it's worth taking a step back to consider why you're building this application and how you should go about it. It's easy to build a cool demo with foundation models, but it's hard to create a profitable product. First, let's evaluate the use case. The first question to ask is why you want to build this application. Like many business decisions, building an AI application is often a response to risks and opportunities. Here are a few examples of different levels of risk, from high to low. First, if you don't build this, competitors with AI could make you obsolete. If AI poses a major existential threat to your business, incorporating it must be your highest priority. This is common for businesses involving document processing and information aggregation, like financial analysis, insurance, and data processing. It's also common for creative work like advertising and web design. Second, if you don't do this, you'll miss opportunities to boost profits and productivity. Most companies embrace AI for the opportunities it brings. AI can help in most, if not all, business operations. It can make user acquisition cheaper by crafting more effective ad copy, improve user retention with better customer support, and help with sales lead generation, internal communication, and market research. Third, you might be unsure where AI will fit into your business yet, but you don't want to be left behind. While a company shouldn't chase every hype train, many have failed by waiting too long to adapt to new technologies. Investing resources into understanding how a transformational technology can impact your business is a good idea if you can afford it. Once you've found a good reason to develop this use case, you should consider whether you have to build it yourself. If AI poses an existential threat, you might want to develop your AI capabilities in-house. However, if you're using AI just to boost productivity, there might be plenty of buy options that can save you time and money while giving you better performance. Next, consider the role of AI and humans in the application. What role AI plays in the product influences its development and requirements. Here are 3 key points to consider. First, is AI critical or complementary? If an app can still work without AI, then AI is complementary. For example, Face ID wouldn't work without AI-powered facial recognition, but Gmail would still work without Smart Compose. The more critical AI is to the application, the more accurate and reliable it needs to be. Second, is the feature reactive or proactive? A reactive feature responds to a user's request, like a chatbot. A proactive feature shows its response when there's an opportunity, like traffic alerts on Google Maps. Reactive features usually need to be fast, while proactive features can be pre-computed, so latency is less of an issue. However, since users don't ask for proactive features, they can be seen as annoying if the quality is low, so they typically have a higher quality bar. Third, is the feature dynamic or static? Dynamic features are updated continually with user feedback, like Face ID, which needs to adapt as people's faces change. Static features are updated periodically, like object detection in Google Photos, which is likely updated only when the app is upgraded. In AI, dynamic features might mean that each user has their own model that is continually fine-tuned on their data. It's also important to clarify the role of humans. Will AI provide background support to humans, make decisions directly, or both? For a customer support chatbot, AI responses can be used in different ways. It could show suggestions for human agents to reference, respond only to simple requests, and route complex ones to humans, or respond to all requests directly. Involving humans in AI's decision-making process is called human in the loop. Microsoft has a framework for gradually increasing AI automation called crawl, walk, run. Crawl means human involvement is mandatory. Walk means AI can interact directly with internal employees. Run means increased automation, potentially including direct AI interactions with external users. The role of humans can change over time as the AI system improves. Next, let's think about AI product defensibility. If you're selling AI applications as standalone products, it's important to consider their defensibility. The low entry barrier is both a blessing and a curse. If something is easy for you to build, it's also easy for your competitors. What moats do you have to defend your product? Building applications on top of foundation models means providing a layer on top of them. If the underlying models expand their capabilities, the layer you provide might be subsumed by the models, making your application obsolete. In AI, there are generally three types of competitive advantages: technology, data, and distribution, the ability to get your product in front of users. With foundation models, the core technologies of most companies will be similar. The distribution advantage likely belongs to big companies. The data advantage is more nuanced. Big companies likely have more existing data, but if a startup can get to market first and gather sufficient usage data to continually improve their products, data will be their moat. There have been many successful companies whose original products could have been features of larger products. Calendly could have been a feature of Google Calendar. MailChimp could have been a feature of Gmail. Many startups eventually overtake bigger competitors by building a feature that those competitors overlooked. Perhaps yours can be the next one. Now let's talk about setting expectations. Once you've decided to build this amazing AI application yourself, the next step is to figure out what success looks like. The most important metric is how it will impact your business. For a customer support chatbot, the business metrics could include what percentage of customer messages you want to automate, how many more messages it allows you to process, how much quicker you can respond, and how much human labor it can save you. It's also important to track customer satisfaction. To ensure a product isn't released before it's ready, have clear expectations on its usefulness threshold, how good it has to be useful. This might include quality metrics for the responses, latency metrics like time to first token, and cost metrics like the cost per inference request. If you're not sure what metrics to use yet, don't worry. The rest of this audiobook will cover many of them. Next is milestone planning. Once you've set measurable goals, you need a plan to achieve them. Evaluate existing models to understand their capabilities. The stronger the off-the-shelf models are, the less work you'll have to do. Planning an AI product needs to account for its last-mile challenge. Initial success with foundation models can be misleading. It might take a weekend to build a fun demo, but it could take months or even years to build a production-ready product. It's easy to get from 0 to 60%, but getting from 60 to 100% becomes exceedingly challenging. A lot of time is spent working on product kinks and dealing with hallucinations. The slow speed of achieving each subsequent 1% gain can be discouraging. Finally, consider maintenance. Product planning doesn't stop at achieving its goals. You need to think about how the product will change over time and how it should be maintained. The AI space is moving incredibly fast, and building on top of foundation models means committing to riding this bullet train. Many changes are good. Context lengths are getting longer, model outputs are getting better, and model inference is getting faster and cheaper. However, even these good changes can cause friction in your workflows. The best option today might become the worst option tomorrow. You'll have to constantly be on your guard and run a cost-benefit analysis for each technology investment. Some changes are easier to adapt to, like swapping one model API for another. However, some changes are harder, especially those around regulations. Technologies surrounding AI are considered national security issues for many countries, meaning resources like compute, talent, and data are heavily regulated. Regulations around intellectual property and AI usage are still evolving. If you build your product on top of a model trained using other people's data, can you be certain that your product's IP will always belong to you? Once you've committed to building an AI product, let's look into the engineering stack needed to build these applications. Next up is the AI engineering stack. The rapid growth of AI engineering has also created an incredible amount of hype and fear of missing out. The number of new tools, techniques, models, and applications introduced every day can be overwhelming. Instead of trying to keep up, let's look at the fundamental building blocks of AI engineering. To understand AI engineering, it's important to recognize that it evolved from ML engineering. When a company starts experimenting with foundation models, it's natural for its existing ML team to lead the effort. Some companies treat AI engineering and ML engineering as the same thing. Others have separate job descriptions for each. Regardless of how organizations position them, their roles have significant overlap. To best understand AI engineering and how it differs from traditional ML engineering, let's break down the different layers of the AI application building process. There are 3 layers to any AI application stack: application development, model development, and infrastructure. When developing an AI application, you'll likely start from the top layer and move down as needed. First is application development. With models readily available, anyone can use them to develop applications. This layer has seen the most action in the last 2 years and is still rapidly evolving. It involves providing a model with good prompts and necessary context and requires rigorous evaluation and good user interfaces. Second is model development. This layer provides tools for developing models, including frameworks for modeling, training, fine-tuning, and inference optimization. Since data is central to model development, this layer also includes dataset engineering. Third, at the bottom of the stack, is infrastructure. This includes tools for model serving, managing data and compute, and monitoring. Data from GitHub shows a big jump in the number of AI tools in 2023 after the introduction of Stable Diffusion and ChatGPT. The categories that saw the highest increases were applications and application development. The infrastructure layer saw some growth, but much less than the other layers. This is expected. Even though models and applications have changed, the core infrastructural needs like resource management and monitoring remain the same. This brings us to an important point. While the excitement around foundation models is unprecedented, many principles of building AI applications remain the same. For enterprise use cases, AI applications still need to solve business problems. You still need to do systematic experimentation. With classical ML engineering, you experiment with different hyperparameters. With foundation models, you experiment with different models, prompts, retrieval algorithms, and more. We still want to make models run faster and cheaper, and it's still important to set up a feedback loop to iteratively improve our applications. This means that much of what ML engineers have learned over the last decade is still applicable. However, there are also many innovations unique to AI engineering, which we'll explore in this audiobook. Now let's compare AI engineering versus ML engineering. While the core principles of deploying AI applications remain, it's also important to understand how things have changed. This is helpful for teams adapting their existing platforms for new AI use cases and for developers who want to stay competitive. At a high level, building applications with foundation models today differs from traditional ML engineering in 3 major ways. First, without foundation models, you had to train your own models for your applications. With AI engineering, you use a model someone else has trained for you. This means AI engineering focuses less on modeling and training and more on model adaptation. Second, AI engineering works with models that are bigger, consume more compute, and have higher latency than in traditional ML engineering. This means there's more pressure for efficient training and inference optimization. It also means many companies now need more GPUs and work with bigger compute clusters, creating a need for engineers who know how to work with them. Third, AI engineering works with models that can produce open-ended outputs. These outputs give models more flexibility but are also harder to evaluate, making evaluation a much bigger problem in AI engineering. In short, AI engineering differs from ML engineering in that it's less about model development and more about adapting and evaluating models. I've mentioned model adaptation several times, so let's clarify what that means. Model adaptation techniques can be divided into two categories, depending on whether they require updating the model's weights. Prompt-based techniques, like prompt engineering, adapt a model without updating its weights. You adapt a model by giving it instructions and context instead of changing the model itself. This is easier to get started with and requires less data. Fine-tuning, on the other hand, requires updating the model's weights. You adapt a model by making changes to the model itself. Fine-tuning techniques are generally more complicated and require more data, but they can significantly improve your model's quality, latency, and cost. Now, let's zoom into the application development and model development layers to see how each has changed with AI engineering. Let's start with model development. This is the layer most commonly associated with traditional ML engineering. It has three main responsibilities: modeling and training, dataset engineering, and inference optimization. Modeling and training refers to coming up with a model architecture, training it, and fine-tuning it. Developing ML models requires specialized knowledge of different algorithms and neural network architectures. With the availability of foundation models, this knowledge is no longer a must-have for building AI applications. However, it's still extremely valuable. It's helpful to understand the difference between a few key terms: training, pre-training, fine-tuning, and post-training. Training always involves changing a model's weights. Pre-training refers to training a model from scratch, where the weights are randomly initialized. For LLMs, this often involves training for text completion and is the most resource-intensive step. Fine-tuning means continuing to train a previously trained model. Post-training is often used to refer to the training a model developer does after the pre-training phase, like making it better at following instructions before release. When an application developer does it, it's usually called fine-tuning. Some people use the term training to refer to prompt engineering, which is not technically correct. If you teach a model what to do through its input context, you're doing prompt engineering. Next is dataset engineering. This refers to curating, generating, and annotating the data needed for training and adapting AI models. In traditional ML engineering, most use cases are close-ended, like spam classification, where the output is either spam or not spam. Foundation models, however, are open-ended. Annotating open-ended queries is much harder. Another difference is that traditional ML works more with tabular data, whereas foundation models work with unstructured data. In AI engineering, data manipulation is more about deduplication, tokenization, context retrieval, and quality control. Finally, there's inference optimization, which means making models faster and cheaper. This has always been important, but as foundation models scale up and incur even higher costs and latency, it has become even more crucial. One challenge is that they are often auto-regressive, meaning tokens are generated sequentially, which can be slow for long outputs. Now let's look at application development. With traditional ML engineering, where teams build their own models, model quality is a key differentiator. With foundation models, where many teams use the same model, differentiation must be gained through the application development process. This layer consists of three main responsibilities: evaluation, prompt engineering, and the AI interface. Evaluation is about mitigating risks and uncovering opportunities. It's necessary throughout the whole model adaptation process. While always important, it's even more crucial with foundation models because of their open-ended nature and expanded capabilities. Prompt engineering is about getting AI models to express desirable behaviors from the input alone without changing the model's weights. It's not just about telling a model what to do, but also about giving it the necessary context and tools to do a given task. AI interface means creating an interface for end users to interact with your AI applications. With foundation models, anyone can build AI applications. You can serve them as standalone products or embed them into other products. There's a need for tools that provide interfaces for these applications or make it easy to integrate AI into existing products. While the chat interface is the most common, Interfaces can also be voice-based or embodied in augmented and virtual reality. The increased emphasis on application development, especially on interfaces, brings AI engineering closer to full-stack development. Traditionally, ML engineering was Python-centric. Today, while Python is still popular, there's increasing support for JavaScript APIs. Many AI engineers are now coming from web development or full-stack backgrounds. An advantage they have is their ability to quickly turn ideas into demos, get feedback, and iterate. With AI models readily available, it's possible to start by building the product first and only invest in data and models once the product shows promise. To summarize this chapter, I've aimed to explain the emergence of AI engineering as a discipline, thanks to the availability of foundation models, and to give you an overview of the process needed to build applications on top of them. We've walked through the rapid evolution of AI, from language models to large language models, then to foundation models, and how this gave rise to AI engineering. We discussed some of the most successful application patterns, both for consumers and businesses. We also covered the important question of whether you should build an application and what to consider before you do. Finally, we looked at the AI engineering stack and how it has changed from traditional ML engineering. While many principles remain the same, AI engineering brings new challenges and solutions. One aspect of AI engineering that's especially hard to capture in writing is the incredible collective energy and creativity of the community. It can be overwhelming to keep up with all the new techniques and discoveries. The more overwhelming a space is, the more important it is to have a framework to help navigate it. This audiobook aims to provide such a framework. The rest of the audiobook will explore this framework step by step, starting with the fundamental building block of AI engineering, the foundation models that make so many amazing applications possible. Chapter 2: Understanding Foundation Models. To build applications with foundation models, you first need foundation models. While you don't need to know how to develop a model to use it, a high-level understanding will help you decide which model to use and how to adapt it to your needs. Training a foundation model is an incredibly complex and costly process, and those who know how to do it well are often bound by confidentiality agreements. This chapter won't teach you how to build a model to compete with ChatGPT. Instead, I'll focus on the design decisions that have a significant impact on downstream applications. With the growing lack of transparency in the training process, it's difficult to know all the design decisions that go into making a model. However, in general, differences between foundation models can be traced back to decisions about their training data, model architecture and size, and how they are post-trained to align with human preferences. Since models learn from data, their training data reveals a great deal about their capabilities and limitations. This chapter begins with how model developers curate training data, focusing on its distribution. Given the dominance of the transformer architecture, it might seem that model architecture is less of a choice. You might be wondering, what makes the transformer architecture so special? How long until another architecture takes over, and what might it look like? This chapter will address these questions. We'll also explore how a model developer might determine the appropriate size for their model. A model's training process is often divided into pre-training and post-training. Pre-training makes a model capable, but not necessarily safe or easy to use. That's where post-training comes in, which aims to align the model with human preferences. But what exactly is human preference? We'll discuss that in this chapter. While most people understand the impact of training on a model's performance, the impact of sampling is often overlooked. Sampling is how a model chooses an output from all possible options. It's a key concept that explains many seemingly baffling AI behaviors, like hallucinations and inconsistencies. Choosing the right sampling strategy can also significantly boost a model's performance with relatively little effort. The concepts covered in this chapter are fundamental for understanding the rest of the audiobook. However, you might already be familiar with some of them, so feel free to skip any section you're confident about. You can always revisit this chapter later if you encounter a confusing concept. Let's start with training data. An AI model is only as good as the data it was trained on. If there's no Vietnamese in the training data, the model won't be able to translate from English into Vietnamese. Similarly, if an image classification model only sees animals in its training set, it won't perform well on photos of plants. If you want a model to improve on a certain task, you might want to include more data for that task in its training. However, collecting enough data for a large model isn't easy and can be expensive. Model developers often have to rely on available data, even if it doesn't perfectly meet their needs. For example, a common source for training data is Common Crawl, a dataset created by a nonprofit that crawls websites on the internet. In 2022 and 2023, this organization crawled approximately 2 to 3 billion web pages each month. The data quality of Common Crawl is questionable. Think clickbait, misinformation, propaganda, and every sketchy website you've ever seen. A study by the Washington Post showed that many of the most common websites in the dataset rank low on trustworthiness scales. In other words, Common Crawl contains plenty of fake news. Yet, because Common Crawl is readily available, variations of it are used in most foundation models that disclose their training data sources, including OpenAI's GPT-3 and Google's Gemini. To avoid scrutiny, many companies have stopped disclosing this information. Some teams use heuristics to filter out low-quality data. For example, OpenAI used only Reddit links that received at least 3 upvotes to train GPT-2. While this helps, Reddit isn't exactly a pinnacle of propriety. This use what we have, not what we want approach can lead to models that perform well on tasks present in the training data, but not necessarily on the tasks you care about. To address this, it's crucial to curate datasets that align with your specific needs. This section focuses on curating data for specific languages and domains. While these models can be trained from scratch, it's also common to fine-tune them on top of general-purpose models. You might wonder, why not just train a model on all available data so it can do everything? Many people do this, but training on more data often requires more computing power and doesn't always lead to better performance. A model trained on a smaller amount of high-quality data might outperform one trained on a large amount of low-quality data. Let's talk about multilingual models. English dominates the internet. An analysis of the Common Crawl dataset shows that English accounts for almost half of the data, making it 8 times more prevalent than the second most common language, Russian. Many other languages, despite having many speakers, are severely underrepresented. Given the dominance of English in the data, it's not surprising that general-purpose models work much better for English than for other languages. For example, on the MMLU benchmark, a suite of multiple-choice problems, GPT-4 performed much better in English than in underrepresented languages like Telugu. Similarly, when tested on math problems, GPT-4 was able to solve them in English more than 3 times as often as in Armenian or Farsi, and it failed on all questions for Burmese and Amharic. Underrepresentation is a big reason for this underperformance. The 3 languages with the worst performance on GPT-4's MMLU benchmarks, Telugu, Marathi, and Punjabi, are also among the most underrepresented in Common Crawl. However, it's not the only reason. A language's structure and the culture it embodies can also make it harder for a model to learn. Since LLMs are generally good at translation, can we just translate queries from other languages into English, get the responses, and translate them back? Many people do this, but it's not ideal. First, it requires a model that can sufficiently understand the underrepresented language. Second, translation can cause information loss. For example, some languages have pronouns that denote the relationship between speakers, and this information can be lost when translated into English. Models can also have unexpected performance challenges in non-English languages. For example, NewsGuard found that ChatGPT is more willing to produce misinformation in Chinese than in English. Besides quality issues, models can also be slower and more expensive for non-English languages. A model's inference latency and cost are proportional to the number of tokens in the input and response. It turns out that tokenization can be much more efficient for some languages than others. For the same meaning, languages like Burmese and Hindi require many more tokens than English or Spanish. This means GPT-4 takes approximately 10 times longer and costs 10 times more in Burmese than in English for the same content. To address this, many models have been trained to focus on non-English languages, such as Chinese, French, Vietnamese, and Arabic. Now let's discuss domain-specific models. General-purpose models like Gemini, GPTs, and Llamas can perform incredibly well across a wide range of domains, including coding, law, science, and business. This is largely thanks to the inclusion of these domains in their training data. Common Crawl, for instance, includes a variety of domains like technology, health, and finance. Even though these models can answer everyday questions about different domains, they are unlikely to perform well on highly domain-specific tasks, especially if they never saw these tasks during training. Two examples are drug discovery and cancer screening. Drug discovery involves protein and DNA data, which is expensive to acquire and unlikely to be found in public internet data. Similarly, cancer screening involves X-ray and fMRI scans, which are hard to obtain due to privacy. To train a model to perform well on these tasks, you need to curate very specific data sets. One of the most famous domain-specific models is DeepMind's AlphaFold, trained on the sequences and 3D structures of around 100,000 known proteins. NVIDIA's BioNeMo is another model that focuses on biomolecular data for drug discovery, and Google's MedPalm 2 combines an LLM with medical data to answer medical queries with higher accuracy. Domain-specific models are especially common in biomedicine, but other fields can benefit from them too. A model trained on architectural sketches could help architects much better than a general model like Stable Diffusion, or a model trained on factory plans could be optimized for manufacturing processes. This section gave a high-level overview of how training data impacts a model's performance. Next, let's explore the impact of how a model is designed. Now let's talk about modeling. Before training a model, developers need to decide what it should look like. What architecture should it follow? How many parameters should it have? These decisions impact not only the model's capabilities, but also its usability for downstream applications. For example, a 7 billion parameter model will be vastly easier to deploy than a 175 billion parameter model. Let's explore the factors behind these decisions. First, let's discuss model architecture. As of this writing, the most dominant architecture for language-based foundation models is the transformer architecture, which is based on a mechanism called attention. It addresses many limitations of previous architectures, which contributed to its popularity. However, it also has its own limitations. This part can get a bit technical, so if it feels too deep in the weeds, feel free to skip ahead. To understand the transformer, let's look at the problem it was created to solve. It came after the success of the sequence-to-sequence, or seek-to-seek, architecture. At the time, seek-to-seek provided a significant improvement on challenging tasks like machine translation and summarization. In 2016, Google incorporated it into Google Translate, which they claimed gave them the largest improvements to date for machine translation quality. At a high level, seek-to-seek has an encoder that processes inputs and a decoder that generates outputs. Both inputs and outputs are sequences of tokens. It uses recurrent neural networks, or RNNs, for both the encoder and decoder. The encoder processes the input tokens one by one and outputs a final hidden state that represents the input. The decoder then generates output tokens one by one based on that final hidden state and the previously generated token. There were two problems with this approach. First, the decoder only used the final hidden state of the input, which is like generating answers about a book using only its summary. This limited the quality of the outputs. Second, because of the RNNs, both input processing and output generation were done sequentially, making it slow for long sequences. The transformer architecture addresses both of these problems with the attention mechanism. Attention allows the model to weigh the importance of different input tokens when generating each output token. This is like generating answers by referencing any page in the book, not just the summary. While the attention mechanism is often associated with the transformer, it was actually introduced 3 years earlier. The Transformer paper's breakthrough was showing that attention could be used without RNNs. The Transformer architecture gets rid of RNNs entirely. With transformers, the input tokens can be processed in parallel, significantly speeding up input processing. However, transformer-based autoregressive models still have a sequential output bottleneck. This means inference for these models consists of two steps: prefill, where the input tokens are processed in parallel, and decode, where the model generates one output token at a time. At the heart of the transformer is the attention mechanism. To understand how it works, we need to look at three types of vectors: query, key, and value. The query vector represents the current state of the decoder. The key vector represents a previous token, like a page number in a book. The value vector represents the actual content of that token, like the content of the page. The attention mechanism computes how much attention to give an input token by performing a dot product between the query vector and its key vector. A high score means the model will use more of that page's content when generating the output. Because each previous token has a corresponding key and value vector, the longer the sequence, the more of these vectors need to be computed and stored. This is one reason why it's so hard to extend the context length for transformer models. The transformer architecture is composed of multiple transformer blocks. Each block contains an attention module and a multi-layer perceptron or MLP module. The attention module consists of 4 weight matrices: query, key, value, and output projection. The MLP module consists of linear layers separated by nonlinear activation functions. The number of transformer blocks is often referred to as the model's number of layers. While the transformer model dominates the landscape, it's not the only architecture. Since deep learning's revival in 2012, many architectures have come and gone. The transformer has been around since 2017, which is a long time in this field. Developing a new architecture to outperform it isn't easy, as the transformer has been heavily optimized. However, there is hope. Several alternative architectures are gaining traction. One is RWKV, an RNN-based model that can be parallelized for training. Another architecture that has shown a lot of promise for long sequences is state space models, or SSMs. Since its introduction in 2021, several techniques have been introduced to make it more efficient and scalable. One notable example is Mamba, which scales SSMs to 3 billion parameters and has shown strong performance on language modeling. Another is Jamba, which interleaves blocks of transformer and Mamba layers to scale up even further. Now let's talk about model size. Much of the AI progress in recent years can be attributed to increased model size. The number of parameters is usually appended at the end of a model's name, like Llama 13b, which has 13 billion parameters. In general, increasing a model's parameters increases its capacity to learn, resulting in better models. The number of parameters also helps us estimate the compute resources needed to train and run the model. For example, a 7 billion parameter model, with each parameter stored using 2 bytes, will need at least 14 gigabytes of GPU memory for inference. However, the number of parameters can be misleading if the model is sparse, meaning a large percentage of its parameters are 0. A type of sparse model that has gained popularity is the mixture of experts, or MOE model. An MOE model is divided into different groups of parameters called experts, and only a subset of these experts is active for processing each token. For example, Mixtral 8x7b is a mixture of 8 experts, each with 7 billion parameters. While it has 46.7 billion parameters in total, only 12.9 billion are active for each token, making its cost and speed similar to a 12.9 billion parameter model. A larger model can also underperform a smaller one if it's not trained on enough data. When discussing model size, it's important to consider the size of the data it was trained on. For language models, a good measurement is the number of tokens in the dataset. As of this writing, LLMs are trained on datasets with trillions of tokens. Meta, for example, used 1.4 trillion tokens for Llama 1, 2 trillion for Llama 2, and 15 trillion for Llama 3. Pre-training large models also requires a lot of compute power. A standardized unit for a model's compute requirement is the FLOP, or floating point operation. For example, GPT-3 175B was trained using over 300 sextillion flops. If you had 256 of NVIDIA's high-end H100 GPUs, it would take you about 7.8 months to train GPT-3 175B, and that's assuming you can use them at their maximum capacity all the time. At 70% utilization, and assuming a cost of $2 per hour for one H100, training GPT-3 75B would cost over $4 million. In summary, there are three numbers that signal a model's scale: its number of parameters, the number of training tokens, and the flops required for training. Now, let's discuss scaling laws and how to build compute-optimal models. I hope the last section convinced you of three things. Model performance depends on model size and dataset size. Bigger models and datasets require more compute, and compute costs money. Unless you have unlimited money, budgeting is essential. You don't want to start with an arbitrarily large model and see how much it costs. You start with a budget and work out the best model performance you can afford. Given a fixed amount of flops, what model size and dataset size would give the best performance? A model that achieves the best performance for a given compute budget is compute optimal. The rule that helps calculate the optimal model size and dataset size is called the chinchilla scaling law, proposed by DeepMind in 2022. They trained 400 language models of various sizes and found that for compute optimal training, you need the number of training tokens to be approximately 20 times the model size. This means a 3 billion parameter model needs about 60 billion training tokens. The model size and the number of training tokens should be scaled equally. For every doubling of the model size, the number of training tokens should also be doubled. This compute optimal calculation assumes that the cost of acquiring data is much cheaper than the cost of compute. The chinchilla paper also proposes another calculation for when the cost of data is significant. The scaling law was developed for dense models trained on predominantly human-generated data. Adapting it for sparse models or synthetic data is an active area of research. It's also important to remember that for production, model quality isn't everything. Some models, like Llama, have suboptimal performance, but better usability because their smaller size makes them easier to work with and cheaper to run. On the topic of model performance, it's worth noting that the cost of achieving a given performance is decreasing. However, the cost of improving performance remains high. Improving a model's accuracy from 90 to 95% is more expensive than improving it from 85 to 90%. A model with a 2% error rate might require an order of magnitude more resources than a model with a 3% error rate. We've assumed that bigger models are better. Are there scenarios where bigger models perform worse? In 2022, Anthropic discovered that, counterintuitively, more alignment training can lead to models that align less with human preference. In 2023, a group of researchers launched the Inverse Scaling Prize to find tasks where larger language models perform worse. They found that larger models are sometimes worse on tasks that require memorization and tasks with strong prior assumptions. Now let's talk about scaling bottlenecks. Until now, every order of magnitude increase in model size has led to an increase in model performance. How many more orders of magnitude can model sizes grow? There are already two visible bottlenecks: training data and electricity. Foundation models use so much data that there's a realistic concern we'll run out of internet data in the next few years. The rate of training dataset size growth is much faster than the rate of new data being generated. If you've ever put anything on the internet, you should assume that it already is or will be included in the training data for some language models. On top of that, the internet is being rapidly populated with data generated by AI models. If companies continue using internet data to train future models, these new models will be partially trained on AI-generated data. Some researchers worry that this could cause new models to gradually forget the original data patterns, degrading their performance over time. The other bottleneck is electricity. Data centers are estimated to consume 1 to 2% of global electricity, and this number is projected to reach between 4 and 20% by 2030. Until we can figure out a way to produce more energy, Data centers can grow at most 50 times, which is less than 2 orders of magnitude. This could lead to a power shortage in the near future, driving up the cost of electricity. Now that we've covered 2 key modeling decisions, architecture and scale, let's move on to the next critical set of design choices: how to align models with human preferences. This brings us to post-training. Post-training starts with a pre-trained model. Let's say you've pre-trained a foundation model using self-supervision. Due to how pre-training works, this model typically has 2 issues. First, self-supervision optimizes the model for text completion, not for conversations. If you input, "how to make pizza," the model might just continue to complete the sentence by adding another question like, "for a family of 6," instead of answering it. Second, if the model was pre-trained on data scraped indiscriminately from the internet, its outputs can be racist, sexist, rude, or just plain wrong. The goal of post-training is to address both of these issues. Every model's post-training is different, but in general, it consists of 2 steps. First is supervised fine-tuning, or SFT. This involves fine-tuning the pre-trained model on high-quality instruction data to optimize it for conversations instead of completion. The second step is preference fine-tuning. This further fine-tunes the model to output responses that align with human preference. This is typically done with reinforcement learning, or RL. Techniques include reinforcement learning from human feedback, or RLHF, which was used by GPT 3.5 and Llama 2, direct preference optimization, or DeepO, used by Llama 3, and reinforcement learning from AI feedback, or RLF, potentially used by Claude. You can think of pre-training as optimizing for token-level quality, where the model is trained to predict the next token accurately. But users don't care about token-level quality. They care about the quality of the entire response. Post-training optimizes the model to generate responses that users prefer. Some people compare pre-training to reading to acquire knowledge, while post-training is like learning how to use that knowledge. Post-training consumes a small portion of the resources compared to pre-training. InstructGPT used only 2% of its compute for post-training. So you can think of post-training as unlocking the capabilities that the pre-trained model already has, but are hard for users to access through prompting alone. Note that a combination of pre-training, SFT, and preference fine-tuning is the popular solution today, but it's not the only one. You can skip any of these steps. Let's start with supervised fine-tuning. As discussed, a pre-trained model is likely optimized for completion rather than conversation. To encourage a model to generate appropriate responses, you can show it examples of appropriate responses. These examples follow a prompt-response format and are called demonstration data. This process is sometimes called behavior cloning. You demonstrate how the model should behave, and the model clones that behavior. Since different types of requests require different types of responses, your demonstration data should cover a range of tasks you want your model to handle, such as question answering, summarization, and translation. Good teachers are important for humans to learn, and similarly, good labelers are important for AIs to learn how to conduct intelligent conversations. Unlike traditional data labeling, which can often be done with little domain expertise, creating demonstration data for complex prompts requires critical thinking, information gathering, and judgment. Companies, therefore, often use highly educated labelers to generate this data. For InstructGPT, nearly 90% of the labelers had at least a college degree. Generating one prompt-response pair can take up to 30 minutes, especially for tasks that involve long contexts like summarization. If it costs $10 for one pair, the 13,000 pairs that OpenAI used for InstructGPT would cost $130,000, and that doesn't include the cost of designing the data, recruiting labelers, and quality control. Not everyone can afford this approach. Some organizations mobilize volunteers to generate data, but this can lead to biases. For example, in one volunteer-led project, 90% of the labelers identified as male. To reduce their dependence on high-quality human-annotated data, many teams are now turning to AI-generated data, which we'll discuss in Chapter 8. Technically, you could train a model from scratch on demonstration data instead of fine-tuning a pre-trained model. but the pre-training approach often yields superior results. Now let's talk about preference fine-tuning. With great power comes great responsibilities. A model that can assist users in achieving great things can also assist them in achieving terrible things. Demonstration data teaches a model to have a conversation, but it doesn't teach it what kind of conversations it should have. For example, if a user asks the model to write an essay about why one race is inferior or how to hijack a plane, should the model comply? In these examples, it's straightforward to most people what a model should do. However, many scenarios are not as clear-cut. People from different backgrounds disagree on many topics, like abortion, gun control, and immigration. How should AI respond to questions about these controversial issues? If your model responds, whatever it says, you'll end up upsetting some of your users. But if it's censored too much, it might become boring and drive users away. The goal of preference fine-tuning is to get AI models to behave according to human preference. This is an ambitious, if not impossible, goal. It assumes that a universal human preference exists and that it's possible to embed it into AI. The earliest successful preference fine-tuning algorithm, which is still popular today, is RLHF. RLHF consists of two parts. First, you train a reward model that scores the foundation model's outputs. Second, you optimize the foundation model to generate responses for which the reward model will give the highest scores. While RLHF is still used, newer approaches like DPO are gaining traction. For example, Meta switched from RLHF for Llama 2 to DPO for Llama 3 to reduce complexity. I'll focus on RLHF here because while more complex, it provides more flexibility to tweak the model. First, let's look at the reward model. RLHF relies on a reward model that, given a prompt-response pair, outputs a score for how good the response is. The challenge, similar to SFT, is getting reliable data. If we ask labelers to score each response directly on a 10-point scale, the scores will vary. An easier task is to ask labelers to compare two responses and decide which one is better. This results in comparison data, which follows the format prompt, winning response, losing response. Even this easier task takes time. It can take 3 to 5 minutes to manually compare two responses, as it requires fact-checking each one. Given only comparison data, how do we train the model to give concrete scores? The solution is to use the right objective function. A common one represents the difference in output scores for the winning and losing responses, and the objective is to maximize this difference. The reward model can be trained from scratch or fine-tuned on top of another model. Some people believe the reward model should be at least as powerful as the foundation model to be able to score its responses. However, as we'll see in the next chapter, a weak model can sometimes judge a stronger model, as judging is believed to be easier than generation. Next, we fine-tune the SFT model using the trained reward model. The goal is to get the SFT model to generate outputs that will maximize the scores given by the reward model. This is often done with an RL algorithm called Proximal Policy Optimization, or PPO. Empirically, both RLHF and DPO improve performance compared to SFT alone. However, there are debates on why they work, and I suspect that preference fine-tuning will change significantly in the future. Both SFT and preference fine-tuning are steps to address the problem created by the low quality of data used for pre-training. If one day we have better pre-training data or better ways to train models, we might not need them at all. Some companies find it okay to skip reinforcement learning altogether. They get their models to generate multiple outputs and pick the ones given high scores by their reward models. This approach, often called the best of N strategy, leverages how a model samples outputs to improve its performance. The next section will shed light on how this works. Now we arrive at the topic of sampling. A model constructs its outputs through a process known as sampling. This section will discuss different sampling strategies and variables, including temperature, top K, and top P. We'll then explore how to sample multiple outputs to improve a model's performance, and how to modify the sampling process to get models to generate responses in specific formats. Sampling makes AI's outputs probabilistic. Understanding this probabilistic nature is crucial for handling AI's behaviors, like inconsistency and hallucination. This section will end with a deep dive into what this probabilistic nature means and how to work with it. Let's start with the fundamentals of sampling. Given an input, a neural network produces an output by first computing the probabilities of possible outcomes. For a classification model trained to identify spam, there are only two outcomes, spam and not spam. The model computes the probability of each, for example, 90% spam and 10% not spam. For a language model to generate the next token, it first computes a probability distribution over all tokens in its vocabulary. When dealing with outcomes of different probabilities, a common strategy is to pick the outcome with the highest probability. This is called greedy sampling. It often works for classification tasks, but for a language model, it creates boring outputs. Instead of always picking the most likely token, the model can sample the next token according to the probability distribution. If red has a 30% chance of being the next token and green has a 50% chance, red will be picked 30% of the time and green 50% of the time. How does a model compute these probabilities? It first outputs a logit vector where each logit corresponds to one possible token. Logits are then converted to probabilities using a softmax layer. Now let's look at some sampling strategies. The right sampling strategy can make a model generate responses that are more suitable for your application. One common strategy is temperature. The problem with sampling according to the probability distribution is that the model can be less creative. In the example, my favorite color is, common colors like red and green will have the highest probabilities. A higher temperature reduces the probabilities of common tokens and increases the probabilities of rarer ones, enabling the model to create more creative responses. Temperature is a constant used to adjust the logits before the softmax transformation. The logits are divided by the temperature. The higher the temperature, the less likely the model is to pick the most obvious value, making its outputs more creative but potentially less coherent. The lower the temperature, the more likely it is to pick the most obvious value, making the output more consistent but potentially more boring. A temperature of 0.7 is often recommended for creative use cases. It's common to set the temperature to 0 for more consistent outputs, which in practice means the model just picks the token with the largest logit. Another strategy is top K. To reduce the computational workload, after computing the logits, we can pick the top K logits and perform softmax only on them. The model then samples from these top values. A smaller K value makes the text more predictable, but less interesting. Top P, also known as nucleus sampling, allows for a more dynamic selection of values. The model sums the probabilities of the most likely next values in descending order and stops when the sum reaches a certain probability, P. Only the values within this cumulative probability are considered. This allows outputs to be more contextually appropriate. We also need a stopping condition. An autoregressive language model generates tokens one after another. A long output takes more time and costs more money. We can ask the model to stop generating after a fixed number of tokens, or when it encounters a stop token, like the end of sequence token. Now, let's discuss test time compute. This is a simple way to improve a model's response quality. Instead of generating only one response per query, you generate multiple responses to increase the chance of getting a good one. One way to do this is the best of n technique, where you randomly generate multiple outputs and pick the one that works best. To pick the best output, you can let users choose, or you can devise a method to select the best one automatically. One method is to pick the output with the highest probability. The probability of an output is the product of the probabilities of all tokens in it. You can pick the one with the highest average log probability. Another method is to use a reward model to score each output. OpenAI also trained verifiers to help their models pick the best solutions to math problems. They found that using a verifier resulted in approximately the same performance boost as a 30 times increase in model size. This means a 100 million parameter model with a verifier can perform on par with a 3 billion parameter model without one. DeepMind has even argued that scaling test time compute can be more efficient than scaling model parameters. In one OpenAI experiment, Sampling more outputs led to better performance, but only up to a certain point, 400 outputs. Beyond that, performance decreased, possibly because the chance of finding adversarial outputs that could fool the verifier also increased. You can also use application-specific heuristics to select the best response. For example, if your application converts natural language to SQL queries, you can have the model keep generating outputs until it produces a valid SQL query. Now let's talk about generating structured outputs. Often, in production, you need models to generate outputs that follow certain formats. This is crucial for two scenarios. First, for tasks that require structured outputs, like converting natural language into a machine-readable format like SQL. Second, for tasks whose outputs are used by downstream applications that need them to be in a specific parsable format. There are several ways to guide a model to generate structured outputs. You can use prompting, post-processing, test-time compute, constrained sampling, and fine-tuning. Prompting is the first line of action, but there's no guarantee the model will always follow your instructions. Post-processing involves writing a script to correct common mistakes a model makes, which can work surprisingly well if the errors are small and predictable. Test-time compute means keep generating outputs until one fits the expected format. Constrained sampling is a technique that guides the generation of text towards certain constraints. At a high level, to generate a token, the model samples only among values that meet the constraints. This requires having a grammar that specifies what is and isn't allowed at each step. Fine-tuning a model on examples that follow your desired format is the most effective and general approach. For certain tasks, you can even modify the model's architecture before fine-tuning, like adding a classifier head for a classification task to guarantee the output format. Now, let's delve into the probabilistic nature of AI. The way AI models sample their responses makes them probabilistic. This means that if you ask an AI model the same question twice, its answer can change. This probabilistic nature can cause inconsistency and hallucinations. Inconsistency is when a model generates very different responses for the same or slightly different prompts. Hallucination is when a model gives a response that isn't grounded in facts. Foundation models are usually trained on a large amount of data. They are aggregations of the opinions of the masses, containing a world of possibilities. Anything with a non-zero probability, no matter how far-fetched or wrong, can be generated by AI. This characteristic makes building AI applications both exciting and challenging. This probabilistic nature makes AI great for creative tasks. What is creativity but the ability to explore beyond the common paths? AI can brainstorm limitless ideas and generate never-before-seen designs. However, this same probabilistic nature can be a pain for everything else. Model inconsistency can be frustrating for users. You can mitigate this by caching answers, fixing the model's sampling variables like temperature and seed, but there's no guarantee of 100% consistency. Hallucinations are fatal for tasks that depend on factuality. In June 2023, a law firm was fined for submitting fictitious legal research to court because they had used ChatGPT, unaware of its tendency to hallucinate. Detecting and measuring hallucinations has been a staple in natural language generation for years. There are currently two hypotheses about why language models hallucinate. The first is that a language model can't differentiate between the data it's given and the data it generates. If a model generates the sentence, "Chip Huyen is an architect," it then treats this as a given fact and can expand upon it, leading to outrageously wrong facts. This is sometimes called snowballing hallucinations. The second hypothesis is that hallucination is caused by a mismatch between the model's internal knowledge and the labeler's internal knowledge. During supervised fine-tuning, models are trained to mimic responses written by labelers. If these responses use knowledge that the labelers have but the model doesn't, we're effectively teaching the model to hallucinate. If we can't stop hallucinations altogether, can we at least detect when a model hallucinates? Detecting hallucinations isn't straightforward, but we'll discuss how to do it in Chapter 4. To summarize this chapter, we've discussed the core design decisions when building a foundation model. We looked at how training data, model architecture, and scale impact a model's performance. We also covered post-training, which involves supervised fine-tuning and preference fine-tuning to align models with human preferences. Finally, we explored sampling, the process by which a model generates output tokens. This probabilistic nature is what makes models like ChatGPT so creative, but also causes issues like inconsistency and hallucinations. Working with AI models requires building your workflows around this probabilistic nature. The rest of this audiobook will explore how to make AI engineering, if not deterministic, at least systematic. The first step toward that is establishing a solid evaluation pipeline, which is the topic of our next chapter. Chapter 3: Evaluation Methodology. The more AI is used, the more opportunity there is for catastrophic failure. We've already seen many failures in the short time that foundation models have been around. A man committed suicide after being encouraged by a chatbot. Lawyers submitted false evidence, hallucinated by AI. Air Canada was ordered to pay damages when its AI chatbot gave a passenger false information. Without a way to quality control AI outputs, the risks might outweigh the benefits for many applications. As teams rush to adopt AI, many quickly realize that the biggest hurdle is evaluation. For some applications, figuring out evaluation can take up the majority of the development effort. Due to the importance and complexity of evaluation, this audiobook has 2 chapters on it. This chapter covers the different methods used to evaluate open-ended models, how they work, and their limitations. The next chapter will focus on how to use these methods to select models and build an evaluation pipeline for your application. While I discuss evaluation in its own chapters, it has to be considered in the context of the whole system. Evaluation aims to mitigate risks and uncover opportunities. To do that, you first need to identify where your system is likely to fail and design your evaluation around those points. Before diving into evaluation methods, it's important to acknowledge the challenges of evaluating foundation models. Because it's difficult, many people settle for word of mouth or just eyeballing the results. This creates even more risk and slows down application development. Instead, we need to invest in systematic evaluation. Since many foundation models have a language model component, this chapter will start with a quick overview of the metrics used to evaluate language models, including cross-entropy and perplexity. These metrics are essential for guiding the training and fine-tuning of language models. Evaluating foundation models is especially challenging because they are open-ended. Using human evaluators remains a necessary option for many applications, but it's slow and expensive. The goal is to automate the process. This chapter focuses on automatic evaluation, which includes both exact and subjective evaluation. The rising star of subjective evaluation is AI as a judge, the approach of using AI to evaluate AI responses. It's subjective because the score depends on what model and prompt the AI judge uses. While this approach is gaining rapid traction, it also invites intense opposition from those who believe AI isn't trustworthy enough for this important task. I'm especially excited to go deeper into this discussion, and I hope you will be too. Let's begin with the challenges of evaluating foundation models. Evaluating machine learning models has always been difficult, and with the introduction of foundation models, it has become even more so. There are several reasons for this. First, the more intelligent AI models become, the harder they are to evaluate. Most people can tell if a first grader's math solution is wrong, but few can do the same for a PhD-level math solution. It's easy to tell if a book summary is bad if it's gibberish, but much harder if it's coherent. To validate the quality of a summary, you might need to read the book first. This means evaluation can be much more time-consuming for sophisticated tasks. Second, the open-ended nature of foundation models undermines the traditional approach of evaluating against ground truths. With traditional ML, most tasks are close-ended, like classification. For an open-ended task, however, there are so many possible correct responses for a given input that it's impossible to create a comprehensive list of them to compare against. Third, most foundation models are treated as black boxes. Details like the model architecture and training data can reveal a lot about a model's strengths and weaknesses. But without those details, you can only evaluate a model by observing its outputs. At the same time, publicly available evaluation benchmarks have proven to be inadequate. Ideally, benchmarks should capture the full range of a model's capabilities. But as AI progresses, benchmarks are becoming saturated very quickly, meaning models achieve perfect scores on them. Last but not least, the scope of evaluation has expanded. With general-purpose models, evaluation is not just about assessing performance on known tasks, but also about discovering new tasks the model can do, some of which might extend beyond human capabilities. The good news is that these new challenges have prompted many new methods and benchmarks. The number of published papers on LLM evaluation grew exponentially in the first half of 2023. In my own analysis of GitHub repositories, I found over 50 dedicated to evaluation as of May 2024. The bad news is that despite the increased interest, investment in evaluation lags behind other areas of AI engineering. Inadequate investment leads to inadequate infrastructure, making it hard to carry out systematic evaluations. This is why many people just eyeball the results, which is not sufficient for iterating on an application. This audiobook focuses on a systematic approach to evaluation. Now let's take a moment to understand language modeling metrics. Foundation models evolved out of language models, and many still have them as their main components. For these models, the performance of the language model component tends to be well correlated with the foundation model's performance on downstream applications. Therefore, a rough understanding of language modeling metrics can be very helpful. Most autoregressive language models are trained using cross-entropy or its relative, perplexity. When listening to discussions about models, you might also hear about bits per character and bits per byte, both of which are variations of cross-entropy. All four metrics are closely related. Recall that a language model encodes statistical information about how likely a token is to appear in a given context. The more statistical information a model can capture, the better it is at predicting the next token. Compared to the rest of the audiobook, this section is a bit math-heavy. If you find it confusing, feel free to skip the math and focus on the discussion of how to interpret these metrics. First, let's talk about entropy. Entropy measures how much information, on average, a token carries. The higher the entropy, the more information each token carries, and the more bits are needed to represent it. Intuitively, entropy measures how difficult it is to predict what comes next in a language. The lower a language's entropy, the more predictable it is. Now for cross-entropy. When you train a language model on a dataset, your goal is to get it to learn the distribution of that data. A language model's cross-entropy on a dataset measures how difficult it is for the model to predict what comes next in that dataset. It depends on two things: the predictability of the data itself and how much the distribution captured by the model diverges from the true distribution of the data. A language model is trained to minimize its cross-entropy. One unit of entropy in cross-entropy is bits. If the cross-entropy of a language model is 6 bits, it means the model needs 6 bits to represent each token. Since different models have different tokenization methods, comparing the number of bits per token isn't fair. Instead, some use bits per character, or BPC. If a token consists of 2 characters on average, a 6 bits per token model has a BPC of 3. A more standardized metric is bits per byte, or BPB, which is the number of bits a model needs to represent 1 byte of the original data. Cross-entropy tells us how efficient a language model is at compressing text. If the BPB of a model is 3.43, it means it can represent each original byte, which is 8 bits, using only 3.43 bits, effectively compressing the text to less than half its original size. Finally, we have perplexity. Perplexity is the exponential of cross-entropy. It measures the amount of uncertainty a model has when predicting the next token. Higher uncertainty means there are more possible options for the next token. What's considered a good value for perplexity depends on the data itself and how perplexity is computed. More structured data, like HTML code, gives lower expected perplexity because it's more predictable. A bigger vocabulary leads to higher perplexity, as there are more possible tokens to predict from. A longer context length leads to lower perplexity, as the model has more information to work with. Besides guiding the training of language models, Perplexity is useful in many parts of an AI engineering workflow. It's a good proxy for a model's capabilities. A model that is bad at predicting the next token will likely perform poorly on downstream tasks. Perplexity can also be used to detect data contamination. If a model's perplexity on a benchmark's data is unusually low, it's likely that the benchmark was included in the model's training data, making its performance on that benchmark less trustworthy. Now let's move on to exact evaluation. When evaluating a model's performance, it's important to differentiate between exact and subjective evaluation. Exact evaluation produces a judgment without ambiguity. For example, a multiple-choice question has a right answer and wrong answers. Essay grading, on the other hand, is subjective. This section covers two evaluation approaches that produce exact scores: functional correctness and similarity measurements against reference data. First, functional correctness. This means evaluating a system based on whether it performs its intended function. For example, if you ask a model to write a function to find the greatest common denominator of two numbers, you can run the generated code to check if it produces the correct result. This is how coding platforms like LeetCode and HackerRank validate submitted solutions. Popular benchmarks for evaluating AI's code generation capabilities, like OpenAI's Human Eval and Google's MBPP, use functional correctness as their metric. A benchmark problem comes with a set of test cases, each consisting of a scenario and the expected output. A model solves a problem if any of the code samples it generates pass all the test cases. The final score, called pass at k, where k is the number of samples generated, is the fraction of solved problems out of all problems. Another category of tasks where functional correctness can be automatically evaluated is game bots. If you create a bot to play Tetris, you can tell how good it is by the score it gets. Next, we have similarity measurements against reference data. If a task can't be automatically evaluated using functional correctness, a common approach is to evaluate the AI's outputs against reference data. For example, if you ask a model to translate a sentence, you can evaluate the generated translation against the correct translation. Generated responses that are more similar to the reference responses are considered better. There are 4 ways to measure the similarity between two open-ended texts. First is exact match, where the generated response must match one of the reference responses exactly. This works for tasks that expect short, exact answers, like simple math problems or trivia questions. Second is lexical similarity, which measures how much two texts overlap. This can be done by counting how many words or n-grams, which are sequences of tokens, they have in common. Common metrics for lexical similarity are blue and rouge. A drawback of this method is that a good response can get a low score if the reference set doesn't contain a similar-looking response. Third is semantic similarity, which aims to compute the similarity in meaning. This first requires transforming a text into a numerical representation called an embedding. The similarity between two embeddings can then be computed using metrics like cosine similarity. This approach doesn't require as comprehensive a set of reference responses, but its reliability depends on the quality of the underlying embedding algorithm. Since the concept of embedding is central to semantic similarity and many other topics in this audiobook, let's take a quick look at what it is. An embedding is a numerical representation that aims to capture the meaning of the original data. It's a vector of numbers. For example, the sentence, "The cat sits on a mat," might be represented by a vector like 0.11, 0.02, 0.54. In reality, the size of an embedding vector is typically between 100 and 10,000. Models trained specifically to produce embeddings include BERT and CLIP. The goal of an embedding algorithm is to produce embeddings that capture the essence of the original data. A good algorithm will produce embeddings where more similar texts have closer embeddings. For example, the embedding of "the cat sits on a mat" should be closer to the embedding of "the dog plays on the grass" than to the embedding of "AI research is super fun." A new frontier is creating joint embeddings for data of different modalities. CLIP, which stands for Contrastive Language Image Pre-training, was one of the first major models to map both text and images into a joint embedding space. In this space, the embedding of an image of a man fishing should be closer to the embedding of the text "a fisherman" than to the embedding of "fashion show." This enables text-based image search. Now let's discuss AI as a judge. If you're enjoying this deep dive into AI evaluation, you can support my future projects by trying a free Audible trial for 30 days. Your support helps me continue creating content like this. Just follow the link in the description. Now, back to our chapter. The challenges of evaluating open-ended responses have led many teams to fall back on human evaluation. But as AI has successfully automated many challenging tasks, can it also automate evaluation? The approach of using AI to evaluate AI is called AI as a judge, or LLM as a judge. An AI model used to evaluate other AI models is called an AI judge. While the idea has been around for a long time, it only became practical with the release of GPT-3 in 2020. As of this writing, it has become one of the most common methods for evaluating AI models in production. Why use AI as a judge? AI judges are fast, easy to use, and relatively cheap compared to human evaluators. They can also work without reference data, which is useful in production environments. You can ask an AI model to judge an output based on any criteria such as correctness, toxicity, or hallucination. Studies have shown that certain AI judges are strongly correlated with human evaluators. In 2023, one study found that the agreement between GPT-4 and humans on their MT-Bench benchmark reached 85%, which was even higher than the agreement among humans, which was 81%. Not only can AI evaluate a response, but it can also explain its decision, which is useful for auditing the results. There are many ways to use AI as a judge. You can use it to evaluate the quality of a response by itself, compare it to reference data, or compare it to another response. A general-purpose AI judge can be asked to evaluate a response based on any criteria. To prompt an AI judge, you should clearly explain the task, the criteria it should follow, and the scoring system, which can be classification, discrete numerical values like 1 to 5, or continuous numerical values. Language models are generally better with text than with numbers, so classification or discrete scoring systems often work better. Prompts with examples have also been shown to perform better. An AI judge is not just a model, it's a system that includes both a model and a prompt, altering any of these results in a different judge. However, there are limitations to this approach. Using AI to evaluate AI can seem circular. The probabilistic nature of AI makes it seem too unreliable to act as an evaluator. For an evaluation method to be trustworthy, its results should be consistent. Yet, the same AI judge can output different scores if prompted differently, or even if run twice with the same prompt. AI judge metrics are also not standardized. Different tools can have very different default prompts for the same criteria, making their scores incomparable. If the AI judge itself is an AI application, it can also change over time, making it hard to track an application's progress. Using powerful models as judges can be expensive. If you use GPT-4 to both generate and evaluate responses, you'll roughly double your API costs. Implementing AI judges in your production pipeline can also add latency. AI judges also have biases. They tend to have a self-bias, where a model favors its own responses. They can have a first-position bias, favoring the first answer in a pairwise comparison. Some also have a verbosity bias, favoring lengthier answers regardless of their quality. What models can act as judges? The judge can be stronger, weaker, or the same as the model being judged. At first glance, a stronger judge makes sense. Using a stronger model as a judge leaves us with two challenges. The strongest model will be left with no eligible judge, and we need an alternative evaluation method to determine which model is the strongest. Using a model to judge itself, or self-evaluation, can be great for sanity checks. If a model thinks its own response is incorrect, it might not be very reliable. Asking a model to evaluate itself can also nudge it to revise and improve its responses. Can the judge be weaker than the model being judged? Some argue that judging is an easier task than generating. A weak model might be able to judge the outputs of a stronger model. A promising research direction is small, specialized judges trained to make specific judgments. Despite its limitations, the AI as a judge approach is versatile and powerful, and its adoption will likely continue to grow. However, it should be supplemented with exact evaluation methods and/or human evaluation. Now, let's look at ranking models with comparative evaluation. Often, you evaluate models not because you care about their scores, but because you want to know which one is the best for you. What you want is a ranking. You can rank models using point-wise evaluation, where you evaluate each model independently and then rank them by their scores. Or you can use comparative evaluation, where you evaluate models against each other and compute a ranking from the comparison results. For responses whose quality is subjective, comparative evaluation is typically easier. It's easier to tell which of two songs is better than to give each one a concrete score. This approach powers the popular Elm's chatbot arena leaderboard, which ranks models using scores computed from pairwise comparisons from the community. Many model providers like ChatGPT also use comparative evaluation to evaluate their models in production by asking users to compare two outputs side by side. For each request, two or more models are selected to respond, and an evaluator, which can be human or AI, picks the winner. A rating algorithm, like Elo or Bradley Terry, is then used to compute a ranking of the models. However, there are challenges to this approach. It's data-intensive, as the number of model pairs to compare grows quadratically with the number of models. If you crowdsource comparisons, it's hard to enforce standardization and quality control. Users might use simple prompts that don't differentiate between models' performance, or they might not have the expertise to judge the responses correctly. Comparative evaluation also doesn't tell you how good a model is or whether it's good enough for your use case. It only tells you which model is better. Despite these limitations, comparative evaluation has many benefits. As models become stronger and surpass human performance, it might become impossible for human evaluators to give concrete scores, but they might still be able to detect a difference, making comparative evaluation the only option. It also aims to capture the quality we care about, human preference. It's also relatively hard to game, as there's no easy way to cheat by training on reference data. To summarize this chapter, we've discussed why foundation models are harder to evaluate and the importance of a reliable evaluation pipeline. We've covered language modeling metrics like perplexity and cross-entropy, and different approaches to evaluate open-ended responses, including functional correctness, similarity scores, and AI as a judge. We also looked at comparative evaluation for ranking models. While many of these methods are promising, no perfect evaluation method exists. It's impossible to capture the ability of a high-dimensional system using one or few-dimensional scores. However, combining different methods can help mitigate many of these challenges. Now that we have a foundation in evaluation, the next chapter will discuss how to use these methods to select models and build an evaluation pipeline for your application. Chapter 4: Evaluate AI Systems. A model is only useful if it works for its intended purposes. You need to evaluate models in the context of your application. The previous chapter discussed different approaches to automatic evaluation. This chapter discusses how to use these approaches to evaluate models for your applications. This chapter has 3 parts. It starts with the criteria you might use to evaluate your applications and how they are defined and calculated. For example, how is factual consistency detected? How are domain-specific capabilities like math and reasoning measured? The second part focuses on model selection. With an increasing number of foundation models to choose from, it can be overwhelming to choose the right one. We'll discuss whether public benchmarks and leaderboards can be trusted and how to select which ones to use. We'll also tackle the question of whether to host your own models or use a model API. The last part discusses developing an evaluation pipeline to guide your application's development over time. This part brings together the techniques we've learned to evaluate concrete applications. Let's start with evaluation criteria. Which is worse, an application that has never been deployed, or an application that is deployed but no one knows if it's working? Most people would say the latter. An AI application with a questionable return on investment is unfortunately quite common. This happens not only because the application is hard to evaluate, but also because developers don't have visibility into how their applications are being used. Before investing time and resources into building an application, it's important to understand how it will be evaluated. I call this evaluation-driven development, inspired by test-driven development in software engineering. In AI engineering, it means defining your evaluation criteria before you start building. This approach makes sense from a business perspective. The most common enterprise applications in production are those with clear evaluation criteria. Recommender systems are common because their success can be evaluated by an increase in engagement or purchases. The success of a fraud detection system can be measured by how much money it saves. While this approach is sensible, focusing only on applications whose outcomes can be easily measured is like looking for a lost key only under the lamppost. We might be missing out on many potentially game-changing applications because there's no easy way to evaluate them. I believe that evaluation is the biggest bottleneck to AI adoption. An AI application should start with a list of evaluation criteria specific to that application. In general, you can think of criteria in 4 buckets: domain-specific capability, generation capability, instruction following capability, and cost and latency. Imagine you ask a model to summarize a legal contract. Domain-specific capability metrics tell you how good the model is at understanding legal contracts. Generation capability metrics measure how coherent or faithful the summary is. Instruction following capability determines whether the summary is in the requested format. Cost and latency metrics tell you how much it will cost and how long you'll have to wait. Let's explore these criteria, starting with domain-specific capability. To build a coding agent, you need a model that can write code. To translate from Latin to English, you need a model that understands both. A model's domain-specific capabilities are constrained by its configuration and training data. To evaluate whether a model has the necessary capabilities, you can rely on domain-specific benchmarks, either public or private. Domain-specific capabilities are commonly evaluated using exact evaluation. Coding-related capabilities are typically evaluated using functional correctness. However, you might also care about efficiency and cost. For example, a SQL query generated by a model might be correct but take too long or require too much memory to run. Non-coding domain capabilities are often evaluated with close-ended tasks, like multiple-choice questions. This is the approach most public benchmarks follow. In April 2024, 75% of the tasks in Eleuther's LM evaluation harness were multiple choice. This is because close-ended outputs are easier to verify and reproduce. Multiple choice questions are popular because they are easy to create, verify, and evaluate against a random baseline. However, a drawback is that a model's performance can vary with small changes in how the questions and options are presented. Despite their prevalence, it's unclear if close-ended benchmarks are a good way to evaluate foundation models. They test the ability to differentiate good responses from bad ones, which is different from the ability to generate good responses. They are best suited for evaluating knowledge and reasoning, but not for evaluating generation capabilities like summarization or translation. Now let's discuss generation capability. In the early days of natural language generation, or NLG, metrics used to evaluate the quality of generated texts included fluency and coherence. As generative models improved, AI-generated texts have become nearly indistinguishable from human-generated texts, so these metrics have become less important. However, they can still be useful for weaker models or for applications involving creative writing and low-resource languages. Generative models, with their new capabilities, have new issues that require new metrics. The most pressing issue is factual consistency, which is crucial for tasks that depend on factuality. Another issue is safety, which is an umbrella term for all types of toxicity and biases. Factual consistency can be verified in 2 settings: against explicitly provided facts, or local factual consistency, and against open knowledge, or global factual consistency. It's much easier to verify against explicit facts. The most straightforward evaluation approach is AI as a judge. More sophisticated AI judge techniques to evaluate factual consistency include self-verification and knowledge-augmented verification. Self-verification relies on the assumption that if a model generates multiple outputs that disagree with one another, the original output is likely hallucinated. Knowledge-augmented verification, like Google DeepMind's SAFE, leverages search engine results to verify the response. It works by decomposing the response into individual statements and then using a search engine to verify each one. Besides factual consistency, there are many ways a model's outputs can be harmful, including inappropriate language, harmful recommendations, hate speech, violence, stereotypes, and biases toward a political or religious ideology. It's possible to use general-purpose AI judges to detect these scenarios. There are also specialized models developed to detect toxicity in human-generated texts that can be used for AI-generated texts. Next is instruction following capability. This asks the question, how good is this model at following the instructions you give it? If a model is bad at it, it doesn't matter how good your instructions are. This is a core requirement for foundation models, and most are trained to do so. Instruction following capability is essential for applications that require structured outputs. For example, if you ask a model to classify an input as A, B, or C, but it outputs, "That's correct," this isn't helpful. It also goes beyond structured outputs. If you ask a model to use only words of at most 4 characters, its outputs should follow that instruction. Benchmarks like Google's IFEval and InfoBench measure a model's capability to follow a wide range of instructions. IFEval focuses on whether the model can produce outputs in an expected format, with 25 types of instructions that can be automatically verified. InfoBench takes a broader view, also evaluating the model's ability to follow content constraints, linguistic guidelines, and style rules. While these benchmarks are helpful, a model that performs well on them might not necessarily perform well on your instructions. You should curate your own benchmark to evaluate your model's capability to follow your instructions using your own criteria. One of the most common types of real-world instructions is role-playing, asking the model to assume a fictional character or persona. This is very common in gaming, interactive storytelling, and writing assistants. Role-playing capability evaluation is hard to automate, but you can use AI as a judge. You should evaluate the role-playing AI on both style and knowledge. Finally, we have cost and latency. A model that generates high-quality outputs but is too slow and expensive to run will not be useful. When evaluating models, it's important to balance quality, latency, and cost. There are multiple metrics for latency for foundation models, including time to first token, time per token, and total latency. It's important to understand what latency metrics matter to you. If you use model APIs, they typically charge by tokens. The more tokens you use, the more expensive it is. If you host your own models, your cost outside of engineering is compute. Now that you have your criteria, let's move on to selecting the best model for your application. Now let's talk about model selection. At the end of the day, you don't really care about which model is the best overall. You care about which model is the best for your application. Once you've defined your criteria, you should evaluate models against them. In general, the selection process involves 2 steps. First, figuring out the best achievable performance, and second, mapping models along the cost-performance axes and choosing the model that gives you the best performance for your budget. When looking at models, it's important to differentiate between hard attributes, which are impossible or impractical for you to change, and soft attributes, which you can and are willing to change. Hard attributes are often the results of decisions made by model providers, like licenses and training data, or your own policies like privacy. Soft attributes are things that can be improved upon, like accuracy or toxicity. At a high level, the evaluation workflow consists of 4 steps. First, filter out models whose hard attributes don't work for you. Second, use publicly available information, like benchmark performance and leaderboard rankings, to narrow down the most promising models. Third, run experiments with your own evaluation pipeline to find the best model. And fourth, continually monitor your model in production. These 4 steps are iterative. you might change a decision from a previous step based on new information. Before we dive into the workflow, let's discuss a question most teams will face: whether to use model APIs or to host models themselves. Let's discuss the build versus buy decision for models. Since most companies won't be building foundation models from scratch, the question is whether to use commercial model APIs or host an open source model yourself. First, let's clarify what open source means for models. The term has become contentious. Originally, it referred to any model that people could download and use. However, some argue that a model should only be considered open if its training data is also publicly available. Open data allows for more flexible model usage and makes it easier to understand the model. To signal whether the data is also open, the term open weight is used for models that don't come with open data, while open model is used for those that do. In this audiobook, for simplicity, I'll use open source to refer to all models whose weights are made public. Another important attribute of open source models is their licenses. Many models are released under their own unique licenses. When evaluating a license, you should ask if it allows commercial use and if there are any restrictions. For example, some licenses require a special agreement for applications with a large number of users. You should also check if the license allows using the model's outputs to train or improve other models. Now, let's compare open source models versus model APIs. For a model to be accessible, it needs to be hosted on an inference service. The interface users interact with is the model API. Commercial models are only accessible via APIs licensed by their developers. Open source models can be supported by any API provider. The answer to whether to host a model yourself or use a model API depends on the use case, and it can change over time. Here are 7 factors to consider: data privacy, data lineage, performance, functionality, costs, control, and on-device deployment. First, data privacy. Externally hosted model APIs are out of the question for companies with strict data privacy policies. There's also a risk that the API provider will use your data to train its models. Second, data lineage and copyright. For most models, there's little transparency about what data they were trained on. The IP laws around AI are also actively evolving. This has driven some companies toward fully open models, whose training data is public, while others opt for commercial models, as the contracts with providers can potentially protect them from data lineage risks. Third, performance. Various benchmarks have shown that the gap between open source and proprietary models is closing. However, it's likely that the strongest open source model will lag behind the strongest proprietary models for the foreseeable future, as companies often keep their best models behind APIs. Fourth, functionality. Many functionalities are needed around a model, like scalability, function calling, and structured outputs. Many of these are challenging to implement, which makes many companies turn to API providers that offer them out of the box. The downside is that you're restricted to the functionalities the API provides. Fifth, cost. Model APIs charge per usage and can get expensive. At a certain scale, a company might consider hosting their own models. However, hosting a model requires significant time, talent, and engineering effort. Sixth, control. If your business depends on a model, you'll want some control over it. With an API, you're subject to their terms and conditions and rate limits. Proprietary models are also more likely to be over-censored, which can be a limiting factor for certain use cases. Finally, on-device deployment. If you want to run a model on-device, third-party APIs are out of the question. Now let's talk about navigating public benchmarks. There are thousands of benchmarks designed to evaluate a model's different capabilities. Aggregating these benchmark results to rank models gives you a leaderboard. There are 2 questions to consider: what benchmarks to include and how to aggregate their results. Due to compute constraints, most public leaderboards can incorporate only a small number of benchmarks. Different leaderboards often end up with different benchmarks, making it hard to compare their rankings. For example, in late 2023, Hugging Face's OpenLLM leaderboard used 6 benchmarks, while Stanford's Helm leaderboard used 10, with only 2 in common. Public leaderboards generally try to balance coverage and the number of benchmarks. However, there's no clarity on what coverage means. An important aspect that's often overlooked is benchmark correlation. If two benchmarks are perfectly correlated, you don't want both of them, as they can exaggerate biases. The results from all the selected benchmarks need to be aggregated to rank models. Hugging Face averages a model's scores on all benchmarks, treating them all equally. Helm, on the other hand, uses mean win rate, which is the fraction of times a model obtains a better score than another model, averaged across scenarios. While public leaderboards are useful, a model that ranks high on a public leaderboard will likely, but not always, perform well for your application. When evaluating models for a specific application, you're essentially creating a private leaderboard. The first step is to gather a list of benchmarks that evaluate the capabilities important to your application. Not all models have publicly available scores on all benchmarks, so you might need to run the evaluation yourself, which can be expensive. Once you have the scores, you need to aggregate them, weighing each benchmark according to its importance to you. As you evaluate models using public benchmarks, keep in mind that they are likely contaminated. This is because data contamination is so common. It happens when a model is trained on the same data it's evaluated on. This can happen unintentionally when models are trained on data scraped from the public internet, which can accidentally include benchmark data. Data contamination undermines the trustworthiness of evaluation benchmarks. To deal with it, you first need to detect it and then decontaminate your data. You can detect contamination using heuristics like n-gram overlapping and perplexity. For model developers, a common practice is to remove benchmarks they care about from their training data before training. Ideally, when reporting a model's performance on a benchmark, they should disclose what percentage of the benchmark data is in their training data. Public benchmarks will help you filter out bad models, but they won't help you find the best models for your application. After using public benchmarks to narrow down to a set of promising models, you'll need to run your own evaluation pipeline to find the best one. How to design a custom evaluation pipeline will be our next topic. Now let's discuss how to design your evaluation pipeline. The success of an AI application often hinges on the ability to differentiate good outcomes from bad ones. To do this, you need a reliable evaluation pipeline. This section focuses on evaluating open-ended tasks. Step 1. Evaluate all components in a system. Real-world AI applications are complex, consisting of many components. You should evaluate the end-to-end output and each component's intermediate output independently. For example, an application that extracts a person's current employer from their resume might have two steps: extracting all the text from the PDF and then extracting the employer from the text. If the model fails, it could be because of either step. For chatbot-like applications, you should evaluate both per turn and per task. Turn-based evaluation looks at the quality of each output, while task-based evaluation assesses whether the system completed the overall task. Step 2. Create an evaluation guideline. This is the most important step. An ambiguous guideline leads to ambiguous scores. You need to define not only what the application should do, but also what it shouldn't do. Start by defining your evaluation criteria. The hardest part is often not determining if an output is good, but rather what good means. For a customer support application, a good response might be defined by 3 criteria: relevance, factual consistency, and safety. For each criterion, create a scoring rubric with examples. What does a response with a score of 1 look like, and why does it deserve that score? Validate your rubric with humans. A clear guideline is the backbone of a reliable evaluation pipeline. Finally, tie your evaluation metrics to business metrics. If your chatbot's factual consistency is 80%, what does that mean for the business? Maybe it means you can automate 30% of customer support requests. Understanding this impact is helpful for planning. Step 3. Define evaluation methods and data. Now that you have your criteria and scoring rubrics, let's define what methods and data you'll use. Different criteria might require different evaluation methods. For example, you might use a small, specialized toxicity classifier for toxicity detection, semantic similarity to measure relevance, and an AI judge for factual consistency. Curate a set of annotated examples to evaluate your application. Use actual production data if possible. You should also slice your data to gain a finer-grained understanding of your system. This means separating your data into subsets like paying users versus free users and looking at your system's performance on each subset separately. This can help you avoid biases, debug issues, and find areas for improvement. How much data you need for each evaluation set depends on the application. The number of examples should be large enough for the result to be reliable, but small enough not to be prohibitively expensive to run. You should also evaluate your evaluation pipeline itself. Is it getting you the right signals? How reliable is it? How correlated are your metrics? And how much cost and latency does it add to your application? Finally, iterate. As your needs and user behaviors change, your evaluation criteria will also evolve, and you'll need to iterate on your evaluation pipeline. Make sure to do proper experiment tracking, logging all variables that could change in an evaluation process. To summarize this chapter, we've discussed the importance of evaluation and the challenges of evaluating open-ended, powerful models. We covered a list of criteria to evaluate models and how to use them to select the best model for your application. We also looked at the pros and cons of hosting a model versus using a model API and how to navigate public benchmarks. The chapter ended with a step-by-step guide on how to create an evaluation pipeline for your application. Now that we have a solid foundation in evaluation, let's move on to the actual model adaptation process, starting with a topic that many people associate with AI engineering: prompt engineering. Chapter 5, Prompt Engineering. Prompt engineering refers to the process of crafting an instruction that gets a model to generate the desired outcome. It's the easiest and most common model adaptation technique. Unlike fine-tuning, prompt engineering guides a model's behavior without changing its weights. Thanks to the strong base capabilities of foundation models, many people have successfully adapted them for applications using prompt engineering alone. You should make the most out of prompting before moving to more resource-intensive techniques. Prompt engineering's ease of use can be misleading. At first glance, it looks like just fiddling with words until something works. While it does involve a lot of fiddling, it also involves many interesting challenges and ingenious solutions. You can think of it as human-to-AI communication. You communicate with AI models to get them to do what you want. Anyone can communicate, but not everyone can communicate effectively. Similarly, it's easy to write prompts, but not easy to construct effective ones. Some argue that prompt engineering lacks the rigor to qualify as an engineering discipline. However, prompt experiments should be conducted with the same rigor as any ML experiment, with systematic experimentation and evaluation. This chapter covers both how to write effective prompts and how to defend your applications against prompt attacks. Before we dive into all the fun applications you can build with prompts, let's start with the fundamentals. Let's begin with an introduction to prompting. A prompt is an instruction given to a model to perform a task. The task can be as simple as answering a question, like "Who invented the number 0?" or more complex, like asking the model to build a website from scratch. A prompt generally consists of one or more of the following parts: a task description, which is what you want the model to do, examples of how to do the task, and the concrete task itself, like the question to answer or the book to summarize. For prompting to work, the model has to be able to follow instructions. How much prompt engineering is needed also depends on how robust the model is to small changes in the prompt. If a small change, like writing 5 instead of 5, causes the model's response to be dramatically different, then more fiddling is needed. As models become stronger, they also become more robust. Teaching models what to do via prompts is also known as in-context learning. This term was introduced in the GPT-3 paper, which demonstrated that language models can learn desirable behaviors from examples in the prompt, even if those behaviors are different from what the model was originally trained to do, all without updating the model's weights. Each example provided in the prompt is called a shot. Teaching a model to learn from examples in the prompt is called few-shot learning. With 5 examples, it's 5-shot learning. When no example is provided, it's 0-shot learning. How many examples are needed depends on the model and the application. In general, the more examples you show a model, the better it can learn, but the number of examples is limited by the model's maximum context length. Many model APIs give you the option to split a prompt into a system prompt and a user prompt. You can think of the system prompt as the task description and the user prompt as the task. For example, if you're building a chatbot that helps buyers understand property disclosures, you can put the instruction to act like a real estate agent in the system prompt, while the user's question and the uploaded disclosure can be in the user prompt. Given a system prompt and a user prompt, the model combines them into a single prompt, typically following a template. Different models use different chat templates, and even the same model provider can change the template between versions. Accidentally using the wrong template can lead to bewildering performance issues. Small mistakes, like an extra new line, can also cause the model to significantly change its behaviors. It's always a good practice to double-check that your inputs follow the model's chat template exactly. Many model providers emphasize that well-crafted system prompts can improve performance. This is likely because the system prompt comes first in the final prompt, and the model might be better at processing instructions that come first, or because the model has been post-trained to pay more attention to the system prompt. How much information can be included in a prompt depends on the model's context length limit. This limit has increased rapidly in recent years, from GPT-2's 1,000 token limit to Gemini 1.5 Pro's 2 million token limit. A 100,000 token context length can fit a moderate-sized book. Not all parts of a prompt are equal. Research has shown that a model is much better at understanding instructions given at the beginning and the end of a prompt than in the middle. This has been demonstrated by a test commonly known as needle in a haystack, where a random piece of information is inserted in different locations in a prompt, and the model is asked to find it. Now that we've discussed what a prompt is and why prompting works, let's discuss the best practices for writing effective prompts. This section focuses on general techniques that have been proven to work with a wide range of models and will likely remain relevant in the near future. First, write clear and explicit instructions. Explain, without ambiguity, what you want the model to do. If you want it to score an essay, explain the score system. If you don't want fractional scores, say so. Ask the model to adopt a persona. A persona can help the model understand the perspective it's supposed to use. For example, if you ask a model to score an essay written by a first grader, asking it to adopt the persona of a first-grade teacher can lead to a more appropriate score. Provide examples. Examples can reduce ambiguity. If you're building a bot to talk to young children, you can provide an example of how to respond to questions about fictional characters like Santa Claus to ensure it gives the desired response. Specify the output format. If you want the model to be concise, tell it so. If you want it to generate JSON, specify the keys. For tasks expecting structured outputs, use markers to mark the end of the prompts to let the model know that the structured output should begin. Second, provide sufficient context. Just as reference texts can help students on an exam, sufficient context can help models perform better. It can also mitigate hallucinations. You can either provide the model with the necessary context or give it tools to gather context, which is the topic of the next chapter. Sometimes you might want to restrict the model's knowledge to only the context provided. This is tricky. Clear instructions like answer using only the provided context along with examples can help. However, prompting alone may not reliably produce the desired outcome. Third, break complex tasks into simpler subtasks. Instead of having one giant prompt for the whole task, each subtask can have its own prompt, and these are then chained together. This not only enhances performance, but also helps with monitoring, debugging, and parallelization. Fourth, give the model time to think. You can encourage the model to think about a question using chain of thought and self-critique prompting. Chain of thought, or COT, means explicitly asking the model to think step by step. The simplest way to do this is to add think step by step to your prompt. Self-critique means asking the model to check its own outputs. Fifth, iterate on your prompts. Prompt engineering requires back and forth. As you understand a model better, you'll have better ideas on how to write your prompts. As you experiment, make sure to test changes systematically. Version your prompts, use an experiment tracking tool, and standardize your evaluation metrics and data. Finally, evaluate prompt engineering tools. Many tools have been developed to aid and automate prompt engineering. Some aim to automate the whole workflow, while others assist with parts of it. These tools can greatly improve your system's performance, but it's important to be aware of how they work under the hood to avoid unnecessary costs and headaches. Always inspect the prompts produced by a tool and track how many API calls it generates. It's also a good practice to organize and version your prompts. Separate your prompts from your code. This helps with reusability, testing, readability, and collaboration. You can organize your prompts in a prompt catalog that explicitly versions each prompt so that different applications can use different versions. Now, let's move on to defensive prompt engineering. Once your application is made available, it can be used by both intended users and malicious attackers. There are three main types of prompt attacks you'll want to defend against. Prompt extraction, where attackers try to extract your application's prompt. Jailbreaking and prompt injection, where they try to get the model to do bad things. And information extraction, where they try to get the model to reveal its training data or information used in its context. These attacks pose multiple risks, including remote code execution, data leaks, social harms, misinformation, service interruption, and brand risk. First, let's talk about proprietary prompts and reverse prompt engineering. Given how much effort it takes to craft prompts, functioning prompts can be quite valuable. Many teams consider their prompts proprietary. The more secretive they are, the more fashionable reverse prompt engineering becomes, which is the process of deducing the system prompt used for an application. This can be done by analyzing the application's outputs or by tricking the model into repeating its entire prompt. While well-crafted prompts are valuable, proprietary prompts are more of a liability than a competitive advantage. Next are jailbreaking and prompt injection. Jailbreaking means trying to subvert a model's safety features, like getting a customer support bot to tell you how to make a bomb. Prompt injection is a type of attack where malicious instructions are injected into user prompts. These attacks are possible precisely because models are trained to follow instructions. As models get better at following instructions, they also get better at following malicious instructions. AI safety is an evolving cat-and-mouse game. There are a few common attack approaches. Direct manual prompt hacking involves manually crafting a prompt to trick a model. This can be done through obfuscation, like intentionally misspelling a keyword, output formatting manipulation, like asking the model to write a poem about an illicit activity, or role-playing, like asking the model to pretend to be a character without safety restrictions. Automated attacks use algorithms to generate prompts that can bypass a model's safety features. For example, Prompt Automatic Iterative Refinement, or PAIR, uses an AI model to act as an attacker, generating and refining prompts until it achieves its objective. Indirect prompt injection is a new, much more powerful way of delivering attacks. Instead of placing malicious instructions in the prompt directly, attackers place them in the tools the model is integrated with, like public web pages or GitHub repositories that the model might access through a web search tool. Then there's information extraction. This is when a model is exploited to reveal sensitive information from its training data or the context it's using. The assumption is that the model memorizes its training data, and the right prompts can trigger it to output its memorization. A recent study demonstrated a prompt strategy that causes a model to divulge sensitive information without the attacker having to know the specific context in which the data appeared. Training data extraction is possible with models of other modalities too. One study showed how to extract over 1,000 images with near duplication of existing images from the open-source model Stable Diffusion. Now let's talk about defenses against prompt attacks. Keeping an application safe first requires understanding what attacks your system is susceptible to. Defenses can be implemented at the model, prompt, and system levels. At the model level, many attacks can be thwarted if the model is trained to better follow system prompts. OpenAI introduced an instruction hierarchy where system prompts have the highest priority, followed by user prompts, model outputs, and finally tool outputs. At the prompt level, you can create prompts that are more robust to attacks. Be explicit about what the model isn't supposed to do. You can also repeat the system prompt twice, both before and after the user prompt, to remind the model of what it's supposed to do. At the system level, you can use isolation, like executing generated code in a virtual machine. You can also require explicit human approval for any potentially impactful commands. You can define out-of-scope topics for your application and filter out inputs that contain predefined phrases associated with those topics. You should also place guardrails on both inputs and outputs to detect suspicious requests and responses containing sensitive or toxic information. To summarize this chapter, we've discussed prompt engineering, the process of crafting instructions to get a model to do what you want. We covered the anatomy of a prompt, why in-context learning works, and best practices for writing effective prompts. We also discussed different prompt attack approaches and potential defenses against them. This chapter focused on writing better instructions. However, to accomplish a task, a model needs not just instructions but also relevant context. How to provide a model with relevant information will be discussed in the next chapter. Chapter 6, RAG and Agents. To solve a task, a model needs both instructions on how to do it and the necessary information to do so. Just like a human is more likely to give a wrong answer when lacking information, AI models are more likely to make mistakes and hallucinate when they are missing context. The last chapter discussed how to write good instructions. This chapter focuses on how to construct the relevant context for each query. Two dominating patterns for context construction are RAG, or Retrieval Augmented Generation, and Agents. The RAG pattern allows the model to retrieve relevant information from external data sources. The Agentic pattern allows the model to use tools like web search and news APIs to gather information. While the RAG pattern is mainly used for constructing context, the Agentic pattern can do much more. External tools can help models address their shortcomings and expand their capabilities. Most importantly, they give models the ability to directly interact with the world, enabling them to automate many aspects of our lives. Both patterns are exciting because of the capabilities they bring to already powerful models. They have captured the collective imagination, leading to incredible demos and products that have convinced many people that they are the future. This chapter will go into detail about each of these patterns, how they work, and what makes them so promising. Let's start with RAG. RAG is a technique that enhances a model's generation by retrieving relevant information from external memory sources. An external memory source can be an internal database, a user's previous chat sessions, or the internet. The retrieve then generate pattern was first introduced in 2017. In that work, the system first retrieved the 5 most relevant Wikipedia pages for a question, and then a model used the information from those pages to generate an answer. The term Retrieval Augmented Generation was coined in 2020. Having access to relevant information can help a model generate more detailed responses while reducing hallucinations. You can think of RAG as a technique to construct context specific to each query, instead of using the same context for all queries. This helps with managing user data, as it allows you to include data specific to a user only in queries related to that user. In the early days of foundation models, RAG emerged as one of the most common patterns, mainly to overcome the model's context limitations. Many people think that a sufficiently long context will be the end of RAG, but I don't think so. First, no matter how long a model's context length is, there will be applications that require even longer contexts. Second, a model that can process a long context doesn't necessarily use that context well. The longer the context, the more likely the model is to focus on the wrong part. RAG allows a model to use only the most relevant information, reducing the number of input tokens while potentially increasing performance. Now let's look at the RAG architecture. A RAG system has two components: a retriever that retrieves information from external memory sources, and a generator that generates a response based on the retrieved information. The success of a RAG system depends on the quality of its retriever. A retriever has two main functions: indexing, which involves processing data so it can be quickly retrieved later, and querying, which is sending a query to retrieve relevant data. To avoid retrieving whole documents, which can be arbitrarily long, you can split each document into more manageable chunks. For each query, the goal is to retrieve the data chunks most relevant to that query. These retrieved chunks are then joined with the user prompt to generate the final prompt, which is then fed into the generative model. Now let's talk about retrieval algorithms. Retrieval is not unique to RAG. It's a century-old idea and the backbone of search engines and recommender systems. At its core, retrieval works by ranking documents based on their relevance to a given query. First, we have term-based retrieval. Given a query, the most straightforward way to find relevant documents is with keywords. A common algorithm is TF-IDF, which combines term frequency, or how many times a term appears in a document, and inverse document frequency, or how informative a term is. Two common term-based retrieval solutions are Elasticsearch and BM25. Next, we have embedding-based retrieval, also known as semantic retrieval. Term-based retrieval computes relevance at a lexical level, which can result in returning documents that are irrelevant to the user's intent. Embedding-based retrievers aim to rank documents based on how closely their meanings align with the query. With embedding-based retrieval, indexing has an extra function, converting the data chunks into embeddings. The database where these embeddings are stored is called a vector database. Querying then involves converting the query into an embedding and fetching the data chunks whose embeddings are closest to the query embedding. Vector search is typically framed as a nearest neighbor search problem. For large datasets, this is usually done using an approximate nearest neighbor, or ANN, algorithm. There are many algorithms and libraries for vector search, such as scan and annoy. Let's compare these retrieval algorithms. Term-based retrieval is generally much faster and works well out of the box. Embedding-based retrieval can be significantly improved over time to outperform term-based retrieval, but it also has its challenges. For example, converting data into embeddings can obscure keywords, making them harder to search for later. A production retrieval system typically combines several approaches, which is called hybrid search. The quality of a retriever can be evaluated based on the quality of the data it retrieves. Two metrics often used are context precision, which is what percentage of retrieved documents are relevant, and context recall, which is what percentage of relevant documents are retrieved. Now, let's discuss retrieval optimization. There are several tactics that can increase the chance of relevant documents being fetched. First is the chunking strategy. How you split your documents into chunks can significantly impact your retrieval system's performance. The simplest strategy is to chunk documents into chunks of equal length. You can also split documents recursively using increasingly smaller units. Overlapping chunks can ensure that important boundary information is included in at least one chunk. There is no universal best chunk size or overlap size. You have to experiment to find what works best for you. Second is re-ranking. The initial document rankings generated by the retriever can be further re-ranked to be more accurate. A common pattern is to use a cheap but less precise retriever to fetch candidates, and then a more precise but more expensive mechanism to re-rank them. Third is query rewriting. For example, if a user asks, "How about Emily Doe?" this query is ambiguous without context. You need to rewrite it to reflect what the user is actually asking, like, "When was the last time Emily Doe bought something from us?" Fourth is contextual retrieval. This involves augmenting each chunk with relevant context to make it easier to retrieve. A simple technique is to augment a chunk with metadata like tags and keywords. You can also augment each chunk with the questions it can answer. The last section discussed text-based RAG systems, but external data sources can also be multimodal and tabular. For multimodal RAG, if your generator is multimodal, its context can be augmented with images, videos, audio, and more. For RAG with tabular data, the workflow is significantly different. It might involve generating and executing an SQL query to retrieve information from a data table and then generating a response based on the SQL result. Now let's move on to agents. Intelligent agents are considered by many to be the ultimate goal of AI. The unprecedented capabilities of foundation models have opened the door to agentic applications that were previously unimaginable. These new capabilities make it finally possible to develop autonomous, intelligent agents to act as our assistants, co-workers, and coaches. The possibilities seem endless, and the potential economic value is enormous. This is an emerging field with no established theoretical frameworks, so this section is a best effort attempt to build a framework from the existing literature. First, an overview. An agent is anything that can perceive its environment and act upon that environment. It's characterized by the environment it operates in and the set of actions it can perform. In an AI agent, AI is the brain that processes information, plans a sequence of actions to achieve a task, and determines whether the task has been accomplished. The set of actions an AI agent can perform is augmented by the tools it has access to. ChatGPT is an agent that can search the web, execute Python code, and generate images. RAG systems are agents, and text retrievers and SQL executors are their tools. Compared to non-agent use cases, agents typically require more powerful models. This is because a task often requires multiple steps, and the overall accuracy decreases as the number of steps increases. Also, with access to tools, agents are capable of performing more impactful tasks, but any failure could have more severe consequences. The success of an agent depends on the tool inventory it has access to and the strength of its AI planner. Let's start by looking at tools. An agent's tool inventory is the set of tools it has access to. Actions that allow an agent to perceive the environment are read-only actions, while actions that allow it to act upon the environment are write actions. There are three categories of tools to consider. First, knowledge augmentation, which includes tools that help augment your agent's knowledge, like text retrievers and web search. Web browsing is crucial for preventing a model from going stale. Second, capability extension. These are tools that address the inherent limitations of AI models. For example, AI models are notoriously bad at math, so giving them access to a calculator can significantly boost their capability. Other tools include calendars, unit converters, and code interpreters. External tools can also make a text-only model multimodal by giving it access to a text-to-image model or an image captioning tool. Third, write actions. These are tools that allow a system to make changes to its environment directly, like sending an email, placing an order, or initiating a bank transfer. These enable a system to do more, but the prospect of giving AI the ability to automatically alter our lives is frightening. Trust in the system's capabilities and its security measures is crucial. Now, let's talk about planning. At the heart of a foundation model agent is the model responsible for solving a task. Complex tasks require planning. The output of the planning process is a plan, which is a roadmap outlining the steps needed to accomplish the task. To avoid fruitless execution, planning should be decoupled from execution. You ask the agent to first generate a plan, and only after this plan is validated is it executed. The plan can be validated using heuristics or AI judges. Solving a task typically involves four processes: plan generation, where the agent comes up with a plan; reflection and error correction, where it evaluates the plan; execution, where it takes the actions outlined in the plan; and another round of reflection and error correction, where it evaluates the outcomes and determines if the goal has been accomplished. An open question is how well foundation models can plan. Many researchers believe that autoregressive language models, by their nature, cannot. However, it's unclear whether this is a fundamental limitation or if we just don't know how to use them the right way yet. The simplest way to turn a model into a plan generator is with prompt engineering. You can provide the model with a list of available actions and examples of how to construct a plan. Many model providers offer function calling for their models, effectively turning them into agents. This allows you to declare a tool inventory, and the model will automatically generate what tools to use and their parameters for a given query. Plans can be of different levels of granularity. A detailed plan is harder to generate, but easier to execute. A higher-level plan is easier to generate, but harder to execute. Plans can also have different control flows, like sequential, parallel, if statements, and for loops. Reflection is crucial for an agent to succeed. It can be done with the same agent using self-critique prompts or with a separate component. The REACT framework, which stands for Reason and Act, introduced the idea of interleaving reasoning and action. At each step, the agent is asked to explain its thinking, take actions, and then analyze the observations. The reflection framework separates reflection into two modules: an evaluator that evaluates the outcome, and a self-reflection module that analyzes what went wrong. Tool selection also requires careful consideration. More tools give the agent more capabilities, but the more tools there are, the harder it is to use them efficiently. You'll need to experiment to find the right set of tools. You can do an ablation study to see how the agent's performance drops if a tool is removed, and look for tools that the agent frequently makes mistakes on. Now let's discuss agent failure modes and evaluation. The more complex a task an agent performs, the more possible failure points there are. First, planning failures. The most common mode is tool use failure, where the agent generates a plan with an invalid tool, a valid tool with invalid parameters, or a valid tool with incorrect parameter values. Another mode is goal failure, where the agent fails to achieve the goal or doesn't follow the constraints. Second, tool failures. This happens when the correct tool is used but the tool output is wrong. It can also happen if the agent doesn't have access to the right tools for the task. Third, efficiency. An agent might accomplish a task, but it might be inefficient. You'll want to track how many steps it needs, how much it costs, and how long it takes. Now let's talk about memory. Memory refers to mechanisms that allow a model to retain and utilize information. It's especially useful for knowledge-rich applications like RAG and multi-step applications like agents. An AI model typically has three main memory mechanisms. First is internal knowledge, which is the knowledge the model retains from its training data. Second is short-term memory, which is the model's context. It's fast to access, but its capacity is limited. Third is long-term memory, which are external data sources the model can access via retrieval. A memory system for AI models typically has two functions: memory management, which is managing what information should be stored in short-term and long-term memory, and memory retrieval, which is retrieving relevant information from long-term memory. Memory management for short-term memory is crucial because of the context length limit. The simplest strategy is first in, first out, or FIFO, where the earliest messages are removed as the conversation gets longer. More sophisticated strategies involve removing redundancy by using a summary of the conversation. Another approach is reflection, where after each action, the agent is asked to reflect on the new information and decide if it should be inserted into memory, merged with existing memory, or replace outdated information. To summarize this chapter, we've discussed how RAG and agent systems function. RAG uses a two-step process to retrieve relevant information and then use it to generate more accurate responses. Agents take this a step further by giving a model access to a wide range of tools, allowing it to plan and execute complex tasks. Both patterns often deal with information that exceeds a model's context limit, necessitating a memory system to manage and use all the information a model has. RAG and agents are both prompt-based methods, influencing a model's quality solely through inputs without modifying the model itself. While they can enable many incredible applications, modifying the underlying model can open up even more possibilities. How to do so will be the topic of the next chapter. Chapter Fine-tuning. Fine-tuning is the process of adapting a model to a specific task by further training the whole model or part of it. The previous chapters discussed prompt-based methods, which adapt a model by giving it instructions, context, and tools. Fine-tuning adapts a model by adjusting its weights. Fine-tuning can enhance various aspects of a model. It can improve its domain-specific capabilities, like coding or medical question answering, and can also strengthen its safety. However, it's most often used to improve a model's instruction-following ability, particularly to ensure it adheres to specific output styles and formats. While fine-tuning can help create more customized models, it also requires more upfront investment. A question I hear very often is when to fine-tune and when to do RAG. After an overview of fine-tuning, this chapter will discuss the reasons for and against fine-tuning, as well as a simple framework for choosing between fine-tuning and alternate methods. Compared to prompt-based methods, fine-tuning has a much higher memory footprint. At the scale of today's foundation models, naive fine-tuning often requires more memory than what's available on a single GPU. This chapter will explain the factors contributing to a model's memory footprint, which is important for understanding the techniques developed to reduce it. A memory-efficient approach that has become dominant is parameter-efficient fine-tuning, or PEFT. We'll explore PEFT and how it differs from traditional fine-tuning, with a particular focus on adapter-based techniques. While prompt-based methods don't strictly require ML knowledge, fine-tuning brings you into the realm of model training, where it is required. This chapter is the most technically challenging one for me to write, and it might also be technically challenging to listen to. If at any point you feel like you're diving too deep into details that aren't relevant to your work, feel free to skip ahead. Let's start with an overview of fine-tuning. To fine-tune, you start with a base model that has some, but not all, of the capabilities you need. The goal is to get this model to perform well enough for your specific task. Fine-tuning is a way to do transfer learning, a concept that focuses on how to transfer the knowledge gained from one task to accelerate learning for a new related task. Transfer learning improves sample efficiency, allowing a model to learn the same behavior with fewer examples. For instance, while training a model from scratch for legal question answering might need millions of examples, fine-tuning a good base model might only require a few hundred. Fine-tuning is part of a model's training process and can take many different forms. As discussed in Chapter 2, there's supervised fine-tuning and preference fine-tuning. You can also do self-supervised fine-tuning, also called continued pre-training, by fine-tuning a model on cheap, task-related raw data before moving on to expensive annotated data. It's also possible to fine-tune a model to extend its context length. Fine-tuning can be done by both model developers and application developers. As an application developer, you'll most likely fine-tune a model that has already been post-trained. The more refined a model is, and the more relevant its knowledge is to your task, the less work you'll have to do. Now let's discuss when to fine-tune. Before jumping into different techniques, it's necessary to consider if fine-tuning is the right option for you. It's generally attempted after extensive experiments with prompt-based methods. The primary reason to fine-tune is to improve a model's quality, both in general capabilities and task-specific capabilities. It's commonly used to improve a model's ability to generate outputs in specific formats, like JSON or YAML. Fine-tuning is especially useful if the model you want to use wasn't sufficiently trained on your task. One interesting use case is bias mitigation. If a base model perpetuates certain biases, exposing it to carefully curated data during fine-tuning can counteract them. Fine-tuning can also be used to create smaller, cheaper, and faster models. A common approach is distillation, where a small model is fine-tuned to imitate the behavior of a larger model using data generated by the large model. A small model, fine-tuned on a specific task, might even outperform a much larger out-of-the-box model on that task. However, there are reasons not to fine-tune. While fine-tuning can improve a model for a specific task, it can degrade its performance for other tasks. This is frustrating if you intend the model for an application with diverse prompts. Fine-tuning also requires high upfront investments in data, hardware, and ML talent. You need data, and annotated data can be slow and expensive to acquire. You need to understand how to train models, including how to choose hyperparameters, monitor the learning process, and debug when something goes wrong. And once you have a fine-tuned model, you'll need to figure out how to serve it. AI engineering experiments should start with prompting. Only explore more advanced solutions if prompting alone proves inadequate. Many practitioners have shared stories of teams insisting on fine-tuning, only to find that refining their prompt experiment process was sufficient for their application. Let's look at the fine-tuning versus RAG debate. The answer depends on whether your model's failures are information-based or behavior-based. If the model fails because it lacks information, a RAG system that gives it access to relevant sources can help. If the model has behavioral issues, like failing to follow an expected output format, fine-tuning might help. In short, fine-tuning is for form and RAG is for facts. If your model has both information and behavior issues, start with RAG. It's typically easier since you won't have to worry about curating training data or hosting fine-tuned models. RAG and fine-tuning aren't mutually exclusive. They can sometimes be used together to maximize performance. The workflow to adapt a model to a task might look like this. First, try to get the model to perform your task with prompting alone. Then, add more examples to the prompt. If the model fails due to missing information, connect it to data sources. If it continues to have information-based failures, you might try more advanced RAG methods. If it has behavioral issues, you can opt for fine-tuning. Finally, you can combine both RAG and fine-tuning. Now, let's look into the number one challenge of fine-tuning, its memory bottleneck. Because fine-tuning is memory-intensive, many techniques aim to minimize its memory footprint. Understanding what causes this bottleneck is necessary to understand how these techniques work. A key factor is the number of trainable parameters, which are parameters that can be updated during fine-tuning. The memory needed for each trainable parameter results from the way a model is trained, using a mechanism called backpropagation. With backpropagation, each training step has a forward pass, where the output is computed, and a backward pass, where the model's weights are updated. During the backward pass, each trainable parameter comes with additional values. Its gradient, which is how much it contributed to the mistake, and its optimizer states, which determine how much it should be readjusted. The more trainable parameters there are, the more memory is needed to store these additional values. You can do a back-of-the-napkin calculation to estimate a model's memory usage. During inference, the memory needed is roughly the model's parameter count times the memory needed for each parameter, plus about 20% for activation values. A 13 billion parameter model with 2 bytes per parameter would need about 31.2 gigabytes of memory for inference. During training, you need memory for the model's weights, activations, gradients, and optimizer states. For a 13 billion parameter model with the atom optimizer and 2 bytes per value, the memory needed for gradients and optimizer states alone would be 78 gigabytes. This is why the memory needed for fine-tuning is typically much higher than for inference. The memory required to represent each value also contributes to the model's memory footprint. Numerical values in neural networks are traditionally represented as float numbers. The most common formats are FP32, which uses 32 bits, and FP16, which uses 16 bits. Reducing the precision of a model, also known as quantization, is a cheap and extremely effective way to reduce its memory footprint. Converting a model from a 32-bit format to a 16-bit format reduces its memory by half. Inference is typically done using as few bits as possible, like 16, 8, or even 4 bits. Training is more sensitive to numerical precision, so it's harder to train a model in lower precision. It's typically done in mixed precision, with some operations in higher precision and some in lower precision. Now let's look at fine-tuning techniques. This section focuses on memory-efficient techniques, which center around parameter-efficient fine-tuning. In the early days, models were small enough for full fine-tuning, where all parameters are updated. As models grew, this became impractical for most. Partial fine-tuning, where only some parameters are updated, can reduce the memory footprint, but it's parameter inefficient, meaning it requires many trainable parameters to achieve performance close to full fine-tuning. This led to the quest for parameter-efficient fine-tuning, or PEFT. The idea is to achieve performance close to full fine-tuning while using significantly fewer trainable parameters. Existing PEF techniques generally fall into two buckets: adapter-based methods and soft prompt-based methods. Adapter-based methods involve adding additional modules or adapters to the model. During fine-tuning, the model's original parameters are kept unchanged, and only the adapters are updated. Soft prompt-based methods modify how the model processes the input by introducing special trainable tokens, or soft prompts. These are continuous vectors that are optimized during the tuning process. By far the most popular adapter-based method is LoRA, which stands for low-rank adaptation. LoRA incorporates additional parameters in a way that doesn't add extra inference latency. It decomposes a weight matrix into the product of two smaller matrices, and then updates these two smaller matrices before merging them back into the original matrix. LoRA is parameter efficient and sample efficient. For GPT-3, LoRA achieves comparable or better performance than full fine-tuning while using only 0.007% of the trainable parameters. Why does it work? Many papers have argued that while LLMs have many parameters, they have very low intrinsic dimensions. Pre-training implicitly minimizes this intrinsic dimension, acting as a compression framework for downstream tasks. To apply LoRA, you need to decide what weight matrices to apply it to and the rank of each factorization. It's most commonly applied to the 4 weight matrices in the attention modules. Studies have shown that a small rank between 4 and 64 is usually sufficient. LoRA not only lets you fine-tune models with less memory and data, but it also simplifies serving multiple models. You can fine-tune a model for each of your customers using LoRA and serve them all with a single base model, only swapping out the small LoRA adapters for each customer. A quantized version of LoRA, called QLoRA, has also been developed. It stores the model's weights in 4 bits but dequantizes them back to a 16-bit format during the forward and backward pass. This allows a 65 billion parameter model to be fine-tuned on a single 48 gigabyte GPU. Now let's talk about model merging and multitask fine-tuning. If fine-tuning allows you to create a custom model by altering a single model, model merging allows you to create one by combining multiple models. The goal is to create a single model that provides more value than using all the constituent models separately. This added value can come from improved performance or a reduced memory footprint. One important use case is multitask fine-tuning. Instead of fine-tuning a model on all tasks simultaneously or sequentially, which can be inefficient or lead to catastrophic forgetting, you can fine-tune a model on different tasks separately and then merge them together. Model merging is also appealing for on-device deployment, where memory capacity is limited. You can merge multiple models for different tasks into one model that can perform all of them while requiring much less memory. Model merging approaches differ in how the constituent parameters are combined. 3 approaches are summing, layer stacking, and concatenation. Summing involves adding the weight values of the constituent models together, either as an average or a weighted average. Layer stacking involves taking different layers from one or more models and stacking them on top of each other. Concatenation involves concatenating the parameters of the constituent models. Finally, let's cover some fine-tuning tactics. The actual process of fine-tuning is more straightforward than the context surrounding it. You need to choose a base model, a fine-tuning method, and a framework. When choosing a base model, it's useful to start with the most powerful one you can afford to explore the feasibility of your task. For fine-tuning methods, if you're just starting, try something like LoRA before attempting full fine-tuning. The method you use also depends on your data volume. Full fine-tuning typically requires thousands of examples, while PEF methods can work with a much smaller dataset. There are many fine-tuning frameworks and APIs that can automate many steps in the process. Doing your own fine-tuning gives you more flexibility, but you'll have to provision the necessary compute. There are also many hyperparameters you can tune to improve fine-tuning efficiency. The learning rate determines how fast the model's parameters change. The batch size determines how many examples a model learns from in each step. An epoch is a pass over the training data. For instruction fine-tuning, the prompt loss weight determines how much prompts should contribute to the model's loss compared to responses. To summarize this chapter, we've discussed fine-tuning, a powerful technique for adapting a model to a specific task. We looked at when to fine-tune, the memory bottlenecks associated with it, and various techniques to make it more efficient, like PEFT and quantization. We also explored model merging as a complementary approach. A comment I often hear from practitioners is that fine-tuning is easy, but getting data for fine-tuning is hard. The next chapter will dive into the challenges of acquiring high-quality data. Chapter 8, Dataset Engineering. The quality of a model depends on the quality of its training data. The best machine learning team in the world with infinite compute can't help you fine-tune a good model if you don't have data. The goal of dataset engineering is to create a dataset that allows you to train the best model, ideally within your allocated budget. As fewer companies can afford to develop models from scratch, more are turning to data to differentiate their AI performance. As models demand more data, data handling becomes more challenging and demands more investment in talent and infrastructure. Data operations have evolved from side tasks to dedicated roles. The data landscape is even more complex than the model landscape, with an ever-growing array of datasets and techniques. This chapter gives you an overview of the data landscape and considerations to take into account when building your own dataset. It begins with data curation, addressing questions like what data you need, how much, and what it means for data to be of high quality. It then discusses techniques for data synthesis and processing. This chapter focuses on post-training data, which is more relevant to application developers, but I'll also include lessons from pre-training data when they are insightful. There are best practices you can follow and tools you can use to automate parts of the process. However, data will mostly just be toil, tears, and sweat. The increasing focus on data has given rise to data-centric AI, as opposed to model-centric AI. Model-centric AI tries to improve performance by enhancing the models themselves. Data-centric AI tries to improve performance by enhancing the data. In reality, meaningful progress often requires investment in both. Let's start with data curation. While not all issues with AI models can be solved with data, data is often a key part of the solution. The right data can make a model more capable, safer, and able to handle longer contexts. Conversely, poor data can cause a model to increase biases and hallucinations. What data you need depends on your task and what you want to teach the model. For self-supervised fine-tuning, you need sequences of data. For instruction fine-tuning, you need data in instruction response format. For preference fine-tuning, you need data in instruction winning response, losing response format. Training data should exhibit the behaviors you want your model to learn. Acquiring high-quality annotations is challenging, especially for complex behaviors like chain-of-thought reasoning and tool use. Generating multi-step responses for chain-of-thought, or COAT, can be tedious. To teach a model to use tools, its training data should include tool use examples. This often requires domain experts to create the data. Data curation isn't just about creating new data. It's also about removing existing data to help a model unlearn bad behaviors. Each application might require data with different characteristics. At a high level, however, data curation follows three criteria: data quality, data coverage, and data quantity. First, data quality. A small amount of high-quality data can outperform a large amount of noisy data. The creators of the Yi model family found that 10,000 carefully crafted instructions are superior to hundreds of thousands of noisy ones. Most people understand the importance of data quality, but what does it mean? In general, data can be considered high quality if it has 6 characteristics: relevant, aligned with task requirements, consistent, correctly formatted, unique, and compliant. Second, data coverage. A model's training data should cover the range of problems you expect it to solve. Real-world users often have a wide range of problems, and the way they express them can vary significantly. Coverage requires sufficient data diversity. Different applications have different dimensions of diversity. A French to English translation tool doesn't need language diversity, but might benefit from diversity in topics and styles. A chatbot that recommends products to global customers needs linguistic and cultural diversity. How do you decide on the right data mix? A simple approach is to choose a mix that reflects real-world application usage. You can also use experiments to find the optimal mix. Third, data quantity. Asking how much data you need is like asking how much money you need. The answer varies widely. At one extreme, LLMs can learn from a single example. At another, some teams have fine-tuned models with millions of examples. How much data you need depends on the fine-tuning technique, task complexity, and the base model's performance. Full fine-tuning typically requires at least thousands of examples, while PEFT methods can work with a much smaller dataset. A simple task will require much less data than a complex one. The closer the base model is to the desirable performance, the fewer examples are needed to get there. Before investing in curating a large dataset, you might want to start with a small, well-crafted one to see if fine-tuning can improve the model. If a small dataset is sufficient, that's great. If no improvement is observed, a bigger dataset will rarely do the trick. Now, let's talk about data acquisition and annotation. The goal of data acquisition is to produce a sufficiently large dataset with the quality and diversity you need, while ensuring your data practices respect user privacy and comply with regulations. The most important source of data is typically data from your own application. If you can create a data flywheel that leverages data generated by your users to continually improve your product, you'll gain a significant advantage. Before investing in creating your own data, check available data sets first. There are many data marketplaces, and some of them might have exactly what you need. However, it's often a mix and match approach. Often, you'll need to annotate your own data for fine-tuning. This is challenging not just because of the annotation process, but also because of the complexity of creating clear annotation guidelines. Now let's discuss data augmentation and synthesis. Data augmentation creates new data from existing data. Data synthesis generates data to mimic the properties of real data. Artificially generated data has a long history in software engineering, gaming, and robotics. With AI being capable of generating data indistinguishable from human-generated data, it's possible to synthesize much more sophisticated data. This makes it easier to generate data and enables more use cases. Why use data synthesis? You can synthesize data to increase quantity, coverage, and quality. You can also use it to mitigate privacy concerns and distill models. There are two traditional data synthesis techniques: rule-based and simulation. Rule-based synthesis uses predefined rules and templates to generate data. You can also procedurally generate new data from existing data by applying simple transformations, like flipping an image or replacing a word with a synonym. Simulation involves creating virtual experiments to collect data. This is common in robotics and for self-driving cars. It allows you to run multiple experiments with minimal costs while avoiding accidents. Now for AI-powered data synthesis. AI can simulate the outcomes of arbitrary programs, and it can simulate humans. AI's paraphrasing and translation abilities can be used to augment existing datasets. AI can also generate data for both pre-training and post-training. For instruction data synthesis, AI can be used to synthesize the instructions, the responses, or both. For example, to train the alpaca model, Stanford researchers started with 175 seed examples and used a GPT-3 model to generate 52,000 more that mirrored them. Given the importance of data quality, it's crucial to verify the quality of synthetic data. This can be done using functional correctness and AI verifiers. Coding-related examples are among the most commonly synthesized data because they can be functionally evaluated. For data that can't be verified by functional correctness, it's common to use AI verifiers. However, there are limitations to AI-generated data. It can be of low quality, and the perceived performance achieved by mimicking might be superficial. There's also the risk of model collapse, where recursively using AI-generated data in training causes irreversible defects in the resulting models. AI generation also obscures data lineage, making it hard to assess a model's commercial viability or trust its performance. One special use case of data synthesis where AI-generated data is required is model distillation. This is a method where a small model, the student, is trained to mimic a larger model, the teacher. The goal is often to produce a smaller, faster model that retains performance comparable to the teacher. Finally, let's talk about data processing. Once you've gathered a raw data set, the first thing to do is inspect it to get a sense of its quality. Plot the distribution of tokens, input lengths, response lengths, and so on. Look at the data to see if the examples make sense. Next, deduplicate the data. Duplicated data can skew the data distribution and introduce biases. There are many forms of duplication, and what's considered a duplicate depends on your definition. Then, clean and filter the data. Remove extraneous formatting tokens, data that isn't compliant with your policies like PII and low-quality data. Finally, format the data. Get it into the right format expected by the model you're fine-tuning. Each model uses a specific tokenizer and expects data in a specific chat template. To summarize this chapter, we've discussed the principles of creating a dataset for training a model. Dataset design follows 3 core criteria: quality, coverage, and quantity. Due to the challenge of acquiring high-quality data, many teams have turned to synthetic data. We explored different techniques for data synthesis and how to evaluate the generated data. Let's say that you've curated a wonderful dataset that allows you to train an amazing model. How should you serve this model? The next chapter will discuss how to optimize inference for latency and cost. Chapter 9, Inference Optimization. New models come and go, but one thing will always remain relevant: making them better, cheaper, and faster. Up until now, this audiobook has discussed various techniques for making models better. This chapter focuses on making them faster and cheaper. No matter how good your model is, if it's too slow, your users might lose patience. If it's too expensive, its return on investment won't be worth it. Inference optimization can be done at the model, hardware, and service levels. At the model level, you can reduce a trained model's size or develop more efficient architectures. At the hardware level, you can design more powerful hardware. The inference service runs the model on the given hardware and can incorporate techniques that optimize models for specific hardware. This chapter discusses bottlenecks for AI inference and techniques to overcome them. It will focus mostly on optimization at the model and service levels with an overview of AI accelerators. It also covers performance metrics and trade-offs. Even if you don't implement these inference optimization techniques yourself, understanding them will help you evaluate inference services and frameworks. Let's start by understanding inference optimization. There are 2 distinct phases in an AI model's lifecycle: training and inference. Training is building a model. Inference is using a model to compute an output for a given input. In production, the component that runs model inference is called an inference server. It's part of a broader inference service, which is also responsible for receiving, routing, and pre-processing requests. There are 2 main computational bottlenecks: compute-bound and memory bandwidth-bound. Compute-bound tasks are limited by the computation needed. Memory bandwidth-bound tasks are constrained by the data transfer rate. Different optimization techniques aim to mitigate different bottlenecks. Inference for a transformer-based language model has 2 steps: prefill and decode. Prefill, where the input tokens are processed in parallel, is compute-bound. Decode, where the model generates one output token at a time, is memory bandwidth-bound because it involves loading large matrices into the GPU. Many providers offer 2 types of inference APIs: online and batch. Online APIs optimize for latency, processing requests as they arrive. Batch APIs optimize for cost. If your application doesn't have strict latency requirements, you can send requests to batch APIs for more efficient processing. Online APIs might offer a streaming mode, which returns each token as it's generated. This reduces the time users have to wait for the first token. Now let's look at inference performance metrics. From the user's perspective, the central axis is latency. For autoregressive generation, latency can be broken down into time to first token, or TTFT, and time per output token, or TPOT. It's more helpful to look at latency in percentiles like P50, P90, and P95, as the average can be misleading. Application developers must also consider throughput and utilization. Throughput measures the number of output tokens per second an inference service can generate. It's directly linked to compute cost. Higher throughput typically means lower cost. Utilization metrics measure how efficiently a resource is being used. Model flops utilization, or MFU, is the ratio of the observed throughput relative to the theoretical maximum throughput of a system. Model bandwidth utilization, or MBU, measures the percentage of achievable memory bandwidth used. Now, let's talk about AI accelerators. An accelerator is a chip designed to accelerate a specific type of computational workload. The dominant type of AI accelerator is the GPU. The main difference between CPUs and GPUs is that CPUs are designed for general-purpose usage, while GPUs are designed for parallel processing. The success of NVIDIA GPUs has inspired many other AI accelerators, like Google's TPU and Intel's Habana Gaudi. There's also a trend towards specialized chips for inference, as inference can account for up to 90% of the machine learning costs for deployed AI systems. A chip's main characteristics are its computational capabilities, memory size and bandwidth, and power consumption. Now let's dive into inference optimization. This can be done at the model and service levels. First, model optimization. This aims to make the model more efficient, often by modifying the model itself. For transformer models, three characteristics make inference resource intensive: model size, autoregressive decoding, and the attention mechanism. Model compression involves techniques that reduce a model's size. This audiobook has already discussed quantization and distillation. Another technique is pruning, which involves removing entire nodes of a neural network or setting the least useful parameters to 0. To overcome the autoregressive decoding bottleneck, several techniques have been developed. Speculative decoding uses a faster but less powerful model to generate a sequence of tokens, which are then verified by the target model. Inference with reference copies tokens from the input to speed up generation in scenarios where there's a significant overlap between contexts and outputs. Parallel decoding attempts to generate multiple future tokens simultaneously. The attention mechanism also has its own optimization techniques. To avoid recomputing the key and value vectors at each decoding step, a KV cache is used to store them for reuse. The KV cache size grows with sequence length and batch size, creating a bottleneck for long contexts. Techniques to make the attention mechanism more efficient include redesigning the mechanism itself, optimizing the KV cache size, and writing kernels for attention computation. Kernels are specialized pieces of code optimized for specific hardware accelerators. Writing them requires a deep understanding of the underlying hardware architecture. A tool that lowers code to run on specific hardware is called a compiler. Compilers bridge ML models and the hardware they run on. Now for inference service optimization. Most service-level techniques focus on resource management. One of the easiest ways to reduce cost is batching, where multiple requests are grouped together. There are three main techniques: static batching, dynamic batching, and continuous batching. Continuous batching is the most efficient, as it allows responses to be returned as soon as they are completed, and new requests can be processed in their place. Another technique is decoupling prefill and decode. Since prefill is compute-bound and decode is memory bandwidth-bound, assigning them to different instances can significantly improve the volume of processed requests while adhering to latency requirements. Prompt caching stores overlapping text segments in prompts for reuse. This is useful for queries that involve long documents or long conversations. Finally, parallelism strategies are the backbone of high-performance computing. Replica parallelism creates multiple replicas of a model to handle more requests. Model parallelism splits a large model across multiple machines. Tensor parallelism splits tensors involved in an operator across multiple devices. Pipeline parallelism divides a model's computation into distinct stages and assigns each to a different device. To summarize this chapter, we've discussed the importance of inference optimization for a model's usability. We looked at performance metrics, AI accelerators, and optimization techniques at the model and service levels. The choice of techniques depends on your workloads and performance requirements. Inference optimization concludes the list of model adaptation techniques covered in this audiobook. The next chapter will explore how to integrate these techniques into a cohesive system. Chapter 10: AI engineering architecture and user feedback. So far, this audiobook has covered a wide range of techniques to adapt foundation models to specific applications. This chapter will discuss how to bring these techniques together to build successful products. Given the wide range of AI engineering techniques and tools available, selecting the right ones can feel overwhelming. This chapter takes a gradual approach, starting with the simplest architecture for a foundation model application and progressively adding components to address its challenges. We can spend eternity reasoning about how to build a successful application, but the only way to find out if it actually achieves its goal is to put it in front of users. User feedback is invaluable for guiding product development, but for AI applications, it has an even more crucial role as a data source for improving models. The conversational interface makes it easier for users to give feedback, but harder for developers to extract signals. This chapter will discuss different types of conversational AI feedback and how to design a system to collect the right feedback without hurting user experience. Let's start with AI engineering architecture. In its simplest form, your application receives a query, sends it to a model, and the model's response is returned to the user. From this simple architecture, you can add more components as needs arise. Step 1. Enhance context. The initial expansion usually involves adding mechanisms to allow the system to construct the relevant context needed by the model. This can be done through various retrieval mechanisms, like text retrieval or tabular data retrieval, or by using tools that allow the model to gather information through APIs like web search. Step 2. Put in guardrails. Guardrails help mitigate risks and protect you and your users. Input guardrails protect against risks like leaking private information to external APIs and executing bad prompts. Output guardrails have two main functions: catching output failures and specifying the policy to handle them. Failures can be related to quality, like malformatted or factually inconsistent responses, or security, like toxic responses or responses that contain private information. Many failures can be mitigated by a simple retry logic. Step 3. Add a model router and gateway. As applications grow to involve more models, routers and gateways emerge to help manage complexity and costs. A router typically consists of an intent classifier that predicts what the user is trying to do and routes the query to the appropriate model or solution. A model gateway is an intermediate layer that allows your organization to interface with different models in a unified and secure manner. It provides a unified interface, access control, cost management, and fallback policies. Step 4. Reduce latency with caches. Caching has long been integral to software applications. There are two major system caching mechanisms: exact caching and semantic caching. With exact caching, cached items are used only when the exact same item is requested. With semantic caching, cached items are used even if they are only semantically similar to the incoming query. Semantic caching can increase the cache's hit rate, but also carries the risk of returning an incorrect response if the system mistakes one query for another. Step 5. Add agent patterns. The applications discussed so far are still fairly simple. Agentic patterns can help you build more complex applications with loops, parallel execution, and conditional branching. A model's outputs can also be used to invoke write actions, like composing an email or placing an order, which allow a system to make changes to its environment directly. Now let's talk about monitoring and observability. Observability should be integral to the design of a product, not an afterthought. The goal of monitoring is the same as evaluation: to mitigate risks and discover opportunities. 3 metrics can help evaluate the quality of your system's observability: mean time to detection, mean time to response, and change failure rate. The metrics you should track are highly application-specific and should be designed around the failure modes you want to catch. You can track model quality metrics, like factual consistency and toxicity, and conversation signals, like the number of turns per conversation and response length. You should also track latency and cost. If metrics are numerical measurements, logs are an append-only record of events. The general rule is to log everything. Traces are reconstructed by linking related events together to form a complete timeline of a transaction or process. Finally, you need an AI pipeline orchestrator. An orchestrator helps you specify how different components work together to create an end-to-end pipeline. It ensures that data flows seamlessly between components. There are many AI orchestration tools, but it's often a good idea to start building your application without one first to avoid adding unnecessary complexity. Now let's move on to user feedback. User feedback plays a critical role in AI applications. It can be used to evaluate performance, inform development, and personalize models for individual users. A well-designed user feedback system is necessary to create the data flywheel we discussed in Chapter 8. Traditionally, feedback can be explicit, like a thumbs up or down, or implicit, inferred from user actions. The conversational interface of many AI applications makes it easier for users to give feedback. Feedback extracted from the content of messages is called natural language feedback. There are several signals you can look for. Early termination, like a user stopping a response generation halfway, is a likely sign that the conversation isn't going well. Error correction, when a user starts a follow-up with "no" or "I meant," is another. Users might also complain about an answer being wrong, irrelevant, or toxic. You can also analyze a user's sentiment throughout a conversation. Other conversational feedback can be derived from user actions. Regeneration, when a user generates another response, might indicate dissatisfaction. The way a user organizes their conversations, deleting, renaming, or sharing, can also be signals. Conversation length can be a positive or negative signal depending on the application. Now let's discuss feedback design. Feedback can and should be collected throughout the user journey. It should be non-intrusive and integrated seamlessly into the user's workflow. You can collect feedback at the beginning of the user journey to calibrate the application. When something bad happens, users should be able to report it. When the model has low confidence, you can ask the user for feedback to increase its confidence. Feedback also has its limitations. It has biases, like leniency bias, where people rate items more positively than warranted, and position bias, where users are more likely to click on the first suggestion. User feedback is also incomplete. You only get feedback on what you show users. This can lead to degenerate feedback loops, where a model's predictions influence the feedback, which in turn influences the next iteration of the model, amplifying initial biases. To summarize this chapter, we've looked at the process of building AI applications as a whole. We discussed a common architecture and how to progressively add components to enhance context, add guardrails, manage multiple models, reduce latency, and enable complex agentic patterns. We also covered the importance of monitoring and observability, and how to design a user feedback system to collect valuable data for improving your models. Many AI challenges are, at their core, system problems. To solve them, it's often necessary to step back and consider the system as a whole. A thorough understanding of the system is essential to solving real problems, unlocking new possibilities, and ensuring safety. This audio adaptation is based on the book AI Engineering, Building Applications with Foundation Models by Huyen. If you've enjoyed listening, you can support my work by trying a free Audible trial for 30 days. Your support helps me create more audio adaptations of valuable technical books. You can find the link in the description. Thank you for listening.